It's true. So how are you finding it?
Love it.
Cool. Why the UK?
Because my fiance is from Hong Kong, so she's getting a B&O visa, and that was the easiest way for us to immigrate together somewhere.
I see. The first, the most useful country that you can both get visas for.
Yes.
Yeah. Okay. Fair enough.
So Red Hat's just a departmental transfer. It was pretty simple. So now I work for Red Hat UK Limited.
Cool. Yeah, I did that once.
Yeah, right. Back in the days.
A few years ago.
It's a sad state of affairs. I have to start caring about UK politics.
Yeah,
Your favorite topic?
Yes.
I see. Next time I see you, I have to bring my flame retardant suit to have a discussion with you about all these topics.
It's fine. I mostly just drink these days.
Actually, everything's been pretty smooth. I got my BRP and everything as soon as I landed.
BRP? Oh,
residency permit.
Cool.
Yeah.
Yeah. Well, you're not one of those bad foreigners, are you?
No, I'm specialized
No, I need gin.
Worker.
You can't drive me to gin at this time of the afternoon, where we'll have this conversation some of the time with less an audience, so I can swear more.
Right. I'm just happy I got in so easily and I can just make my life here.
Yeah, cool.
So everything's good. So if anyone's looking for a good place to immigrate, it's nice here if you can get in. David, what's car ownership like here?
In London,
Yeah.
daft. Why would you keep half a ton of metal to annoy you on the streets when you can just use?
There's still part of me that's an American and wants like the sense of freedom by having an automobile.
But if you get into an automobile and you attempt to drive it in the streets of London, then freedom is not the thing that you're going to feel.
Exactly.
Really. Now, if you want to get out into the country and go to other places, sure, right?
It's a good
idea. I mean, we
idea.
find that when we go into the US, right? There are some places, some cities where just why would you bother hiring a car, and other places you would, right? London is not one, unless you want to leave London, right? So yeah, there are loads of people who kind of move out of London and then say, oh, now I'm going to get a car.
I see.
But in London, it's not that I've ever tried living in London. I don't really do cities, right? But yes, those who have lived in London have always said, no, there's just no point, right?
I see. I'll have to reevaluate because I can't even apply for a driver's license until I've been here for 6 months.
But you can drive on your existing one for 6 months.
Yes, I can.
More than that, right? Yeah. I think it's up to a year on an out-of-country 364
like that.
Isn't it? And then you have to leave the country for a day before coming back, and then you can drive for another.
Reset that timer, yeah.
Something weird like that.
But I'm not so sure I would get sold a car with the out-of-country driver's license. That's the thing.
Oh, you'll have no problems buying it. There's nobody really cares. You don't have to have a license at all to buy a car. There's no
right to own a car.
Buying a lethal weapon or something. Yeah, I think registering it is also relatively simple. I don't think you have to have
Much paperwork.
like that. It's just registering the car. It's not really tied to being allowed to be here or anything like that.
Actually, getting a bank account and credit cards was the most challenging as an expat.
Yes.
I needed a bank account to pay my rent, to rent a new apartment, but they wanted a permanent address to open the bank account. It's just endless loop of dependencies, constantly working away, chipping away dependencies.
Yes, I remember. I can't remember now whether it was somebody moving from the US to the UK or vice versa and having similar problems and not being able to pay his rent, not because he didn't have the money, but because he didn't have it here in this form, and
Right.
nobody would give it to him. And I think we just went and got lots of cash out and just handed it to him to go and pay your rent this month so you have somewhere to live. Hopefully, you can sort this all out in less than a month so that you can pay next month's rent.
Mm-hmm.
Yes, it's no fun.
Yeah, money issues are like no fun at all. Hopefully over time I'll have a banking history here and they'll give me credit.
Yeah. Yes, it's painful not even being able to get a credit card that you can book flights on.
Right? I feel like I wasted all that time building up my credit record in the US, which was pretty good, and then coming here and having to start from base bottom.
Yes, even if it's the same bank in name, it's still a different bank.
They
don't know you.
They don't know me.
Well, you might have been good with dollars. We have no idea that you're good with pounds. You're a different person.
I guess we'll get started in about 10 minutes. I can make another espresso for people who missed the first one, but you know what? One stroke was enough for me. Hey, what's up? I'm downstairs. I'm on the conference right now. Okay. Talk to you later. So I plan to go through these introductory slides to like welcome everyone to the conference and just discuss basic details of how the track's going to be run. And then it's not going to take long. So maybe I'll talk about some networking maintenance stuff and maybe do a Q&A if people want to ask questions. Yeah, ask me anything you want about my espresso setup. I'm sure everyone's interested in how to make really good coffee at home. I know I was. It even has an app, and I can put it into standby mode. Let's do that. So now the boiler is in standby, and I can put it back on anytime I want. There's even a statistics page. It's pretty cool. You can control the pre-infusion and post-infusion settings and everything like that on the boiler, temperature, everything you want. Okay. Enough coffee tech. Wait. Nice to see a lot of familiar names. It's too bad we couldn't meet in person because it's just not feasible right now. But those days will come again, right? So David, sorry to bug you, but is this being recorded right now? Or is it not till 2:40?
I believe it is already recorded. I think it's all basically the BBB session is recorded.
I see. Cool.
But it's probably not being live streamed yet.
I see.
And it will probably also be edited out, right? By the time we upload the actual sessions annotated to YouTube later.
Mm-hmm.
Yeah, I suspect that will be edited out. So effectively, no, for most purposes, it's not being recorded. But if we really wanted, to see what you just said, we could find that.
So I'll just wait for 2:40 and then we'll get going. Okay, it looks like the live stream is going, so I guess we can get started. This is the Networking and BPF track for Linux Plumbers 2021 virtual edition for the second year in a row, unfortunately. I know everyone would like to get together in person, but this is not feasible at this current point in time. I'd like to welcome everyone and thank you for participating. For those who are submitted a talk or are presenting, I really appreciate your contribution because the content is what really makes this conference what it is. So we're over 5 days, 4 hours each day, covering 5 talks, 25 talks in total. So I'd like to list the technical committee for 2021. That's me, Daniel, Jakob, Eric, Alexi, and Andre. Thank you everyone for helping review all the submissions and making this conference as good as it can be. So everyone gets about I would ask everyone to please be considerate and stay within your allotted time slot, or else other people have less time to present, and that's really not fair. So let's not do that, okay? You can ask questions in the meeting room via live audio or public chat. If you ask questions in the chat, the moderator will choose them and read them aloud so that the people watching the live stream can understand the question too. And the schedule is at this link. Everything's pretty straightforward. And after our tracks end on Monday and Friday, that's when the LPC keynotes will be. So you can switch over there after the end. Okay. Slides, papers, and videos are at this link. And we'll add links to the video stream later. So we hope that despite being virtual, you enjoy this week of presentations, have fun and learn something new, and help us make networking and BPF development move forward even further than it's already gone. Thank you to the LPC sponsors for making this event happen too. They really make this possible. So that's it for the conference slides. I'll talk about a few things. So run BPF, that's right. Limited edition, you wish you had it, right? Last October, I think most of you heard that I suffered a stroke. It was not very fun. Let me tell you, the list of things I want to experience in life, that's like down at the bottom of the pile, right? But unfortunately, it did happen. That's the negative part. The good part is I had Jakob to back me up at that time. So I'm pretty sure that networking development was undisturbed by my health crisis, which is really great. So Jakob's to be commended for taking the reins during that time, and even not knowing when I would be back, like what kind of time frame it would be for him to have to run the networking tree every day. So we have to thank him for that. So I'm pretty much back. I'm healthy, I feel good, but the only thing is my left hand is not completely back yet. This thing is not typing anything. So I do everything with one hand. I type everything with my right hand. And now that we're both active, we're covered through many time zones. So when I wake up here in London, I man the networking tree. And then once I get the backlog down to a certain amount, this is usually around noon, 1, 2 o'clock, I pass things over to Jakob, and he maintains the tree through the rest of the day in the Pacific time zone, which is great. So any hour of the day, there's someone manning the tree, it seems. So that's good. I really appreciate all the hard work everyone does on the networking. I mean, seriously, I could not do this myself at all. It's just not possible. And I feel an enormous responsibility keeping the tree going and making sure everything's quality moving forward. So thank you everyone for all your participation and help. So if anyone wants to get on the mic and ask a question, I'll be happy to answer it. Just turn your mute off and ask. I'll be more than happy to entertain a question. Everyone's too shy. No one wants to ask anything.
you hear me?
Andrew, I can hear you.
Okay, so I know on the mailing list there's been a bit of frustration said about how fast patches are getting merged. It used to be they were on there for about 3 days. Now it can be 2 or 3 hours, which for those who actually want to review stuff doesn't give them much time. So what is the new policy?
So that's a good question. I'm glad you asked it. One of the many side effects of having a stroke is you become like sort of impatient and impulsive, and it's showing in, I guess, this area. I feel your pain, but at the same time, so I've been trying to back off a little bit on that. And a couple of days ago, I put 2 patches into the need act state, and I just was like, until someone reviews this, I'm not applying it. And those patches who rotted there for like 7 days, I had to just review them myself and apply them anyway. So I understand your frustration, but I'm equally frustrated with people like really just not. I know once a patch is like 2 or 3 days old, after that point, it's past everyone's memory. People aren't going to review it. So there's kind of a balance I need to find in how long is too long. It's probably about 2 days. I think at the 2-day point, if no one's even responded to the patch or said anything about it at all, not even a reviewed by or an act, then probably I need to take matters into my own hands. So if 2 or 3 days is about what you would like to see for patches getting reviewed, I can try to stick to that.
Yeah, it seemed to work well when we had about 3 days. That allows people to go off on the weekend and come back Monday morning and do stuff.
Yeah, weekends are tricky too.
Yeah, real life gets in the way sometimes to reviewing stuff. I know it varies from drivers to drivers. Some are very siloed and nobody cares. Others have got active maintainers and they are going to review it and they need a couple of days to do it.
But like if it's a typo fix or something, I'm putting it right in. You can't be mad about that.
No, that's fine. It's just when there's actual real code.
Like we're adding new APIs to the file layer.
Yep.
I gotcha. I definitely hear you loud and clear on that, and I will definitely make adjustments moving forward.
That would be great. Thanks.
Thanks for the feedback. I appreciate it. Anyone else? So while someone looks for the courage to ask, I have to go get my time cards. Be right back. Okay, the LPC committee has been nice enough to give us these time cards. So this will go up when you have 5 minutes left, 3 minutes, 1 minute. And then when you see this, you really got to wrap things up and be done because you're starting to eat into the break time or the next time slot, which is not cool. So I'll have these available for me right here. Okay. So no one else wants to ask any questions? So all the slides are loaded up here. I can make them active and then select the person to be the presenter. So maybe I'll put Alan's slides up. Alan, you're the presenter now. Whenever you're ready, just get going. I'll mute myself meanwhile.
Great, thanks, David. Can you hear me okay? Great, okay. I'm just going to check the slides are moving for me. Oh, they are not. Hang on. Yep, there we go. Okay. So my name's Alan McGuire. I work in the Linux kernel networking team at Oracle, and I'm going to be talking about BPF tracing and how we can make some improvements there. Let me just share my webcam as well. Okay. Now, working. Okay. So the kind of idea behind this talk is that GDB for debugging has a deep history of making debugging software easier. But as the world gets more parallel, which is clearly what's happening, a lot of problems aren't as amenable to that kind of linear form of debugging that GDB supports. So I'm thinking of cases like, race conditions and time-sensitive issues where BPF tracing is really the right solution because it's such low overhead and, we can collect information from multiple threads. But of course, then BPF tracing isn't quite as feature-rich as something like GDB at this point. So I'm going to talk about some of the features we could look at adding, mainly through additions to the BPF type format. But of course, in doing so, it's important to bear in mind what the trade-offs are. In that context. So principally with the BPF type format, the compact nature of it is the key thing, because you want to carry that around with your running kernel. So keeping things small is very important. So I'm going to be talking about that a little bit as we move through. So I've kind of ordered things in terms of the sort of complexity of the task and what the cost is. So I'm going to be talking about how to display data structures in depth, how to maybe look at including macros in the BPF type format, maybe look at inline functions as well as a potential thing we could represent in the BPF type format. I mean, the Linux kernel is heavily inline, so if you've ever used a tracer, you've probably had that moment of frustration when you tried to trace a function and you realized it wasn't there because it had been inlined. So, are there ways we could help with that that experience? And then finally, to get to the sort of extreme case, local variable representation. I mean, it probably seems ridiculous to do something there, but it's worth looking at what the constraints are in that space too. So if you use GDB, you've probably used its print command, which is very useful for examining data. So we can see using dwarf, it can look at the type associated with the variable and print out the various content of that variable in depth, which is nice. So libbpf has already provided ways of dumping data structures. You've used this probably if you've done BPF tracing to generate a header, a kernel header. So one of the kind of pain points when you were doing BPF development traditionally was having to include a bunch of kernel header files, and sometimes they wouldn't like each other and you get compilation failures. So one of the nice things that was added was the capability to actually dump all of the kernel data structures to a header file using BPF tools. So basically the BPF type format that you carry around with your kernel is just unfolded recursively, so you get all the various types that you might need in your program. And as part of that, with a huge amount of help from Andre, and thank you for that, we recently added a way of dumping not just the type information, but typed data representations. So the idea there is that if you've got a piece of data that you want to look at, and you know what type that data is, you can use those interfaces to solve that problem. So you use the BTF ID associated with the type, and then you get a dump of that data. So to just give an example, here's an skbuff, and we can see it's kind of similar to that output from GDB I showed earlier. So you can see not only the various elements of the data structure, you can also see the values associated with that as well. So this is actually in libbpf now. I think it was in 5.14 it landed. So that capability is there now. So you can use that. And for the future, it would be nice if we could integrate some of that with some of the existing tracing technology that we have. So things like BPF trace and perf and BPF based gtrace, which is under development as well. to kind of help with that process, I tried to create a tool called K-Snoop, which is basically just a kind of a way of exhibiting this capability. So the kind of idea of K-Snoop is just to be able to trace arguments and return values of kernel functions. So it gives you the full argument data and return value data associated with function entry and return. And that's been merged into, if you've ever used BCC, it's in the libbpf tools there. So the libbpf tools in BCC aren't, they aren't using Python, they aren't using any of that, they're using libbpf directly and Bpf skeletons to actually just give you one binary, which will solve whatever problem you have. So it's just kind of a proof of concept idea that allows you to unfold all that data. So sort of, things we could do with that. One of the things that the K-Snoop tool supports is capturing data from a specific set of functions, so which when they're called in a specific order. So, for example, if you had syscaller, a syscaller failure with a particular stack signature, it would be useful to be able to see what the arguments were to those functions as they kind of as your system kind of went on its way to failing. So, one idea would be that as part of syscaller's operation, it encounters a failure, tries to create a reproducer, and then you get the information about the failure and the reproducer. So because we have the stack signature for that failure, we could use that deep data structure analysis to actually add probes for the various functions, and then we could capture that data. So not only would you get a stack trace effectively when you actually got that failure information, you could actually get the arguments to the functions as they occurred. And as I said, K-Snoop has some functionality that does this as well. So the idea is that if we use the -s option there, it allows us to capture, function 1 eventually calls function 2, which calls function 3, and then finally calls function 4. And if we see that sequence in any thread, we'll get basically we're storing the information as we go through that stack of functions. And if we hit the end function, having hit all the other functions along the way, we get output from that, but only in that case. So it's a way of basically saying, if you see this stack signature, give me the arguments and return values associated with that, if anything did return. So that's one possibility. Just integrating that kind of deep data inspection to some of our kind of bots and tools would be interesting. I think would be useful. Another thing we could potentially look at is a diff style output. So, one of the things you might want to do, particularly if you're doing something like watch point based analysis, where you're dealing with data corruption and you don't know who's doing what, or you want to figure out how your data structure is changing, perhaps as you step through a function, which you could do with tracing as well. You could, one option we could look at is expanding the options available to that data dumping to support passing a template data with a associated size as well into the function. And where fields differed from the template, they'd be outputted in a diff style output. So it's just trying to bring some of the capabilities that we have in analyzing code to the data that we use as well. So I think there's a lot of options here we could explore. So this is just to try and suggest a couple of ideas in that direction. This might be a good point to pause before we go on to the next section, just in case there's any questions or comments. Let me just see there. The chat, I'm not seeing anything on the chat at the moment, so if there are any questions, maybe somebody could let me know. The chat seems to be hung for some reason.
Alan, real quick, I think your sound is, or your gain is kind of high.
Oh, sure.
Yeah, because I've been going from conference to conference, and yours really, really loud compared to everyone else.
How's that? Is that a bit better?
A little bit better, maybe a little bit lower.
Sure.
Right. Yeah. That sounds better.
Great.
Much better.
Thank you. Thanks for letting me know. So if there's no other questions, we might keep moving. So as I said, when we're running BPF programs, we could generate a header from the BPF type format information to capture all those types from the kernel. And split BTF actually allows us to do this for modules too, so we can capture module data structures as well, which is really nice. So that header generation process and the compile once run everywhere capability, which allows us to build our binary once and it'll run on different kernel versions using BTF to figure out what the offsets of data structures are. And along with the BPF tool skeleton functionality, which is really nice because that actually allows us to embed our BPF program in the user space binary, which I find to be very handy. So the idea is, rather than having a user space program and a BPF program you've got to carry around, you actually get to embed your bytecode in your user space program as well. So all those things have really added up to make a BPF program development much easier. There's a lot less wrestling with kernel headers, but there is still one time you need to do that, and that's when we're dealing with hash defines and macros. There is a way to do this, and again, harking back to GDB had to wrestle with this problem as well. So to help with that, GCC actually supports an option, -G GDB3, to add debug macro sections to Dwarf. So for example, if we've got some definitions there, they get added to that debug macro section via these macro define indirect tags. So GDB uses this then, so you can actually reference some of the macros in your debugging, so it can be useful there. But for our purposes, it would be useful to have things like constant value definitions, so we don't have to redefine them, and or we don't have to include the kernel headers that define them. So that makes life a lot easier. But then, of course, the big question that looms over all of these things is, what's the cost? So when we look at VM Linux built with that option, there's 1.6 million definitions, which is a lot, obviously. But most of these are duplicated because they're the consequence of including headers in various objects that comprise the VM Linux binary. So the same header file can be included multiple times. So when you deduplicate all of that, we end up with a number around 80,000, which is a lot more tractable. So to encode that in BTF, really what we need to do is encode the name. So the name is basically just the macro name, and then the value is just the string associated with the value. So there's a fairly straightforward way we could do that using a struct BTF type, which is the kind of base type that we use to encode information in BTF. And if we do that with those sort of 80,000 odd definitions, the VM Linux BTF size grows by about 3.3 megabytes. So the test that I did, it started off as about 6.3 megabytes, and then when we added that information, it grew to about 9.6 megabytes. So we're talking a growth, certainly, but not an order of magnitude or anything like that. So it's not a massive addition. But there are some caveats to this whole process. So we need some rules in processing macros, because not only do we have to deduplicate identical definitions, we have to worry about cases where there can be non-identical definitions. So across the whole kernel, there can be multiple definitions of a particular macro. So one approach is basically just not to include any macros which have multiple conflicting values. Another thing that you might want to do as well is avoid encoding macros which have an associated undef with them. These can be used in some cases, like the kbuild mod name definition for a module name, for trace macros as well. Sometimes the undefs are being used. So in general, it's a signal that something clever is being done, and we kind of want to avoid clever in this case, because a lot of the time things won't compile if things are too clever. The other thing you want to do is look at excluding config variables, because core, the call once run anywhere framework actually has a way of representing them as variables. So having config macros as well can cause collisions with those. So we don't want that. And then there's a couple of definitions you probably want to exclude as well. So when you do all of that, you end up with about 68,000 definitions. And then for split BTF, we have to consider that as well, because with split BTF, you've got the base BTF and then the BTF associated with the module. And you could imagine a situation where you'd have a definition in a module that differed with the definition in the core kernel BTF. So we have to consider that case too. So the way I'm proposing this is done is, a set of heuristics like that. But to be honest with you, this is going to require a bit of trial and error, and the trial and error that I'm proposing that we use is to actually try and build as many of the BPF tracing programs in the BPF cell tests using vmlinux.h with macro support, because in doing that we will likely run across a lot of the problems. There's a couple of hundred files there, so in doing that we can see some of the problems that can crop up when we're using macro definitions. So what I'm proposing is the vmlinux.h would have a guarded section for the types, the standard vmlinux _h section. So that would be all the types. And then following that would be a guarded section for VM Linux macros .h. So in that case, that macro section wouldn't exist. If there are no macros defined, that macro section wouldn't be there. So you can use the lack of presence of that macro section and the lack of define of VM Linux macros H as a way of having your program handle the case where BTF macro information wasn't there. So if you've got an existing BPF program, the idea would be you can kind of handle the case where you don't have BTF macros by using that definition as a kind of guard. So here's an example. So this is a BPF program under self-tests. And we can see here that there's a bunch of definitions, and this is the kind of classic copy and paste that you have to do if you don't want to actually include the header files themselves. So we can see if the VM Linux macros H aren't present in vmlinux.h, we need to go and define these directly. Otherwise, we don't have to worry about that. So that's kind of the best case scenario. We can run into problems with name collisions and definitions and so forth. So I think there's going to be a little bit of trial and error here. We're going to have to probably add more things to that exclude list that cause problems. It's not going to be a perfectly clean solution. I think it's going to be one of those things where practice will show up a lot of the problems that could crop up if we do choose to add the macro information. So the other thing is, of course, when we're dealing with macro definitions, we want to think about compile once, run everywhere. So having that define change for different kernel versions is going to be a problem, because if a flag is defined as one thing in one kernel and something else in another, ideally we'd want compile once, run everywhere to take care of that for us transparently. So the trick would probably be to do something like what's done for config parameters, to have some kind of way of representing those flag values or numeric values as variables which are instantiated with the whatever the current type for that value is, and then hopefully the BPF could look at the ELF section with all that data and potentially rewrite those values based on the running kernel. So it would have to use the BPF type format and take the string definitions associated with the values and convert them to the appropriate type. So there'd be a bit of work to be done to do this, and it would probably only be valuable for cases like that where we're dealing with things like flags, which can change from kernel to kernel. So let's see, I think that kind of brings us to the end of talking about macros. So as I say, this is kind of work in progress. I'd hope to get the RFC patch set out this week, but I'm kind of aiming to get the conversions of all the BPF self-tests using this done first, because I think that's the real proof of concept of this idea. And there's a bit of feedback between that process and figuring out what the right set of rules are for determining, what macros get included, what macros get skipped. So I'm hoping to have that sent out later this week. So with that, there would be an RFC patch for the dwarves, PA Hull tool to handle the dwarf to BTF conversion for the macros, and then there's the BPF and BPF side for actually handling the macro representations. So yeah, I'm hoping to get that sent out later this week. But the basics do work. It's just going to be a question of how useful this is in practice, because obviously if the macro definitions are causing problems with too many BPF programs due to defining things that then collide with data structure definitions or whatever, it's not going to be useful in practice. And that's the aim here, to basically make a BPF developer's life easier. So I think we're just going to have to see how that plays out. So if anyone's got any questions or comments or suggestions, maybe I'll just pause for a minute there and we can wait.
Hi Alan, can you hear me?
Yeah, I can, Lawrence.
Brilliant. Hi, my name is Lawrence. I work on a Go library for eBPF, kind of a user space. So that's kind of my point of view. I was wondering, maybe I missed it. Do you have an idea how to encode the names of arguments for macros?
So the approach that I've taken is quite simplistic. So the name of the macro is basically everything before, in the case of macros that are parameterized, the name is everything before the opening bracket of that parameter list. And then the value encompasses the parameter list and the values and the rest of the macro itself. So it's very simplistic, but that does seem to do the trick. It does work in practice. Did you have any thoughts on, is there a situation where having a separate encoding of parameters would be helpful, or?
I don't know. I was just wondering how you do it. The thing is with I guess if you just use the name as it is, it works well if you end up generating C code from that, like the linux.h, but it doesn't give us much more metadata to work with. So we could say, oh, this is actually a macro that has these two arguments, and then you could try and find those in the body, for example. But that's I guess that kind of goes to my next question is for Bpf Core. We also have an implementation for that, and maybe it would be possible to kind of distinguish a macro that has an expression value from a macro that is a constant. I don't know how tricky that would be.
Yeah, that's the thing. And, there's other cases you can think of from a core perspective that would be useful, like, field accessors. A lot of macros have, simplify the field accessors. So in those kind of cases, you would like core to step in and deal with those cases. But again, it's kind of tricky to think of a way to disambiguate things like that in a very clear way. So yeah, it's a hard problem. I mean, I think in that case, a lot of the time you'd probably just fall back and defining your own version of the field access using the core, the Bpf core read or whatever. But yeah, it's hard to know how much metadata to associate with the macro. The argument, certainly the idea of it being a parameterized macro would probably be useful to know.
Sorry, maybe I didn't phrase my question very good. Like, I guess the metadata that you get is from Dwarf, I imagine. Is that right?
Yeah.
How much metadata does Dwarf have about macros? Like, what's the maximum we could put in there, I guess, is my way of asking. Like, if it's clear from the metadata you get from Dwarf that this is actually something that is constant, like that is defined as a macro, but it is a constant. Is that something you could see from the Dwarf, or do you have to kind of dig into that yourself?
Yeah, it's just a string. You just get a string back from Dwarf, as far as I know. So there isn't much metadata we can make use of there, unfortunately.
Okay, cool. Thank you.
No problem. So we might move on to inline functions. So as I mentioned, one of the things that can happen when you're doing tracing is when you try and trace a function, you get a not found error, and that's due to the fact that a lot of functions in the Linux kernel are inlined. So there's no good solution for tracing them currently, but we have to remember that we can trace most instructions by using the K-probe of the function and the offset. So if we had addresses for the inline sites, we could potentially attach K-probes to fire for all the instances of an inline function. So ideally, what we'd like is to have a way of specifying an inline function in the same way as we specify non-inline functions. So, the K-probe slash inline function name. And perhaps if we wanted a specific site, you could do inline function at containing function. So, whatever the function is that function was inlined into, we can maybe specify just that case as wanted. So again, Dwarf comes to the rescue for GDB. So GDB knows about inline information from Dwarf. So would it be feasible to augment BTF with that information? So one way you could do it would be to encode inline sites associated with the function. So the way you could encode that potentially would be something like the BTF ID of the calling function, and then the offset within that calling function where that inline function was inline to, and then perhaps the length of the inline function as well. So the way you could approach that would be to have, for the BTF function definition, so there's a BTF kind func, so that could use a flag to specify an inline. And in the case that it is an inline function, the length, the info VLN associated with that BTF type could specify the number of sites, the inline sites associated with that function, so that inline function. So each of those sites, again, would be the BTF ID of the caller, the offset, and the length of the inline within that call function. And the reason you need that length is because the way it's inline from function to function can vary slightly. So it's good to know how much of that function is actually represented by the inline function side. So with that encoding, the operation would be, when you're dealing with a K-probe, would be, we'll look up the function. If it's not there, If it's in KL sims, we know it's a real function, and if it's not, we can look up that BTF kind func, and if it's marked as an inline, as we talked about previously, we can say for each of those inline sites, we attach a K-probe at the caller's address and offset. So that would be one way to implement that. So the idea is that you can go from inline function to inline sites quite easily. So that's the kind of goal of that encoding mechanism. So when I ran some experiments here, and this could be could be my own lack of ability in using the elfutils libraries, it seemed like there was a lot of information missing for inline sites. So for the VM Linux image, there are about 36,000 inline functions. For those, there's about 86,000 sites which have the kind of program counter values for the start and end, which are basically what we would use to identify, which functions they fall within. There's another 215,000 though that don't have those values. So in those cases, things would be incomplete. And obviously, a concern here would be if you're actually specifying a probe for all the inline sites associated with a function, you don't want to just deal with 40% of them, so, or even less than that. So we need to look into that a little bit more and figure out what's going on there. So we need to think again in terms of BTF. What's the cost of encoding all this stuff? So if we talk about 16 bytes for each of those BTF kind func representations, and then 16 bytes per inline site, we end up at about 1.86 megabytes for the smaller list, the 86,000. And I think the numbers are on there, but the total will be about 5 megabytes for the possible inline sites. So that would assume that we could actually get that inline information about where those inline sites are for all of the inlines that are available in the Linux kernel. So, we're talking about between 2 and 5 megabytes for that inline information. So, so that's sort of the number to bear in mind when we think about the costs here. Now, the other thing to mention here is, when we're at an entry point to a function, the struct pt register, the register information, we can pull out the arguments of that function very easily. And that's obviously not true when we're diving into the middle of a function. So given that that's the case, it may not be necessary, for a traditional function in BTF, we have the function representation, which is the name, and then it points at a prototype for the function, which has all the type information about the arguments or return values. So if we can't make use of that prototype, it might not be necessary to encode it. Because, as I say, we can't make that simple mapping from types of arguments to register values. Because, like I say, we're in the middle of a function. So, there's no simple mapping there. And it's going to vary from inline site to inline site. So the other thing to mention is if we were doing an inline representation for split BTF, the same function name could be in both the base and the split. So in that case, you'd need to have a representation of it in both places because there could be inline sites in both the core kernel and then kernel module as well. So you need to have a kind of double representation there that you wouldn't have in classic BPF functions or BTF functions, which would be deduplicated in that case because they'd be identical. Because the sites are going to be different, we need to preserve a representation in both cases. That would be the kind of wrinkle there. So I want to just pause for a minute there again, just in case anyone has any comments or suggestions there. But I haven't really investigated this in practice. This is more sort of laying out the theoretical possibilities. So we see we're talking about 5 megabytes in terms of cost at the upper end, and the benefit here is that we get to see in a little bit more detail what's going on in terms of the execution path. The problem is, of course, as I mentioned here previously, that we don't have easy access to the arguments of these inline functions. So that's something to bear in mind on the kind of cost side of the ledger as well.
And inline functions subject to optimizations throughout the caller, so they will potentially be the code will be rearranged, not actually the inline function anymore.
Yeah, maybe that's what's going on in some of the cases where we're not seeing any program counter information.
Hello. Hi,
Hello?
Alan. Hi. I have a hi. I have a question about the inline function. So that the inline function can be splitted. Sometimes there's a split the inline function into the function, so that it depends on the inline function line number. The inline function body will be mixed with the caller function code. How can you handle that case?
Yeah, I think I'm going to have to spend a bit more time on this aspect of it. The kind of assumption here is that there's an obvious kind of place where the code's been inlined, and we can just attach there. But yeah, I'll need to investigate a bit further on this, I think.
Yep. Okay. Actually, that are currently the K probes from the F-trace side. I made a path probe to find that such kind of issues. So currently we are using the debug information directory, but if we use our BTF, that is some issuing point. Yeah.
Okay.
Yeah, thank you.
Thanks, Mr. So just to finish things off quickly, and this is where we kind of delve into what's probably not feasible. So, BTF has information about global variables, for CPU variables, function arguments, return values. So the only missing thing from a variable perspective is local variables. So if we were attaching to within the body of a function, that would be useful. Obviously, having information about what's in what register and how that maps to variables would help us ask questions such as, if we're at a K-probe with an entry, what do the registers contain? You can imagine we could have a BPF helper for that, for a particular offset within a function. So, if we got to the point where we can figure that out, we're kind of at the true instruction level tracing state where, we can attach to an arbitrary point to the function and figure out what's going on. So it's more a sort of theoretical endpoint than something that's probably practical in the near future. But to run the numbers, so there's about 2 million variable instances within the dwarf for the core kernel. So even without location information, we're talking about over 30 megabytes for just the struct BTF type information there. So that's kind of an order of magnitude bigger than the current BTF. So, to me, that doesn't seem feasible because the whole, part of the sell here for BTF is that it's small. And, this is kind of pushing it away from that quite significantly. So are there alternatives? Well, from BTF, we know information about the argument registers and return values. So perhaps we could build some sort of graph of how register values evolve during the execution of a function. Perhaps there's something in the verifier that does that kind of type tracking that we could use to kind of repurpose to actually scan kernel functions rather than BPF code in this way. So obviously that's going to leave some things out because some local variables won't be connected if we have a graph. If you imagine that kind of graph from tracking register states. So some things won't actually connect to that. So some local variables might need to be represented in that model. And maybe if we did want to encode something, they'd be the ones to encode the things that we can't actually dynamically infer. So, the conclusion there would be, I think we probably need to look at some kind of dynamic inference methods to actually get information at an instruction level. It's probably not feasible to encode all of that ahead of time. So just to summarize, I mean, we've made the BPF has made huge strides in observability and usability. BTF has been a big part of that. It can grow further capabilities, and tools like GDB are a great source of ideas because they've had to wrestle with some similar problems in the past. But in doing any kind of assessment, the cost benefit always has to respect the key values in BTF, which are size and simplicity, and as a kind of corollary of those, it always has to be present in running kernels. So when we're getting to that sort of more expensive representation, we may need to look at having some sort of hybrid dynamic static methods for creating descriptions. That might be the only way to really get to that instruction level tracing.
Is there a way to actually, I was wondering, is there a way to actually make it so you could get all this information and load it as a module, so you could be like, if for those that don't need to load it, and if you want to, you can either have it dynamically added as a module that has all the information that you could need. And then
that's a really nice idea. Yeah, that's one way to do it, because obviously, 30 megabytes for some systems is way too much, whereas for other people it's not a big deal at all. So yeah, that's a nice potential compromise. Absolutely. So there's just a few references, and that's going to be done. So as I said, I was hoping to get that RFC patch set for BPF Next and Dwarves sent out ahead of the talk. So I'll hopefully get that sent out before the end of the week, because I think it lays out the issues there in terms of representing macros a little bit more clearly. And we can, by looking at how it makes life easier for the self-tests, we can probably it's probably clearer what the costs and benefits are there.
Yeah, it's really interesting. Like, I actually did GDB development, and I didn't know about the GGDB switch until I looked into the text cases and how they worked. So it is a very not so documented feature of GDB, and not many people know about it. So Alan, if you're done, we could do some Q&A.
Sure.
Okay. Anybody got questions? Let's test the chat, make sure I can get a posting in there.
There's been issues with the chat, so I don't know.
Yeah, because apparently it's making all the new accounts as we try to use it the first time instead of like ahead of time.
Yeah, I apologize. I can't actually see the chat at the moment, so if anything pops up there, do let me know.
Sorry, it took me a while to figure out how to enable the microphone. You have to join with microphone. So I wanted just to mention that me and Yonghong are attacking like this VM Linux.h plus macro problem from a slightly different angle. We are looking at actually extending the Clang to allow two different type definitions to coexist. Because like the biggest problem is like not that people want, well, okay, that's one perspective, right? Like I think the biggest problem is not that people really need like some macro to be available in VM Linux.h. The bigger problem is that you cannot include any other kernel header with VM Linux.h, right? So we are trying to attack this problem as by essentially like allowing to have like conflicting type definitions, but marking one of them as sort of like the main one and everything else as like the weak definitions. So when you include VM Linux.h first, and then you include some of the existing kernel headers second, if they have some like redefinitions of type task struct and stuff like that, we'll just, well, not we, but the compiler will just ignore the second one. So that way you get access to all the macroses and static inline function definitions and stuff like that. So just be aware that there is a separate work thread for that. Does it make sense?
Yeah, absolutely. No, that sounds great. Yeah, we have a similar problem with the macros, because one of the things that happens is if you define all the macros, you get all the guards associated with those header files defined. So they're obviously macros themselves. So one of the questions I'm kind of wondering about is, do we include the header guards? Because obviously, if you then include a kernel header file, you've already defined the guards. So if that's included afterwards, then you don't get any of those definitions. So there is, there's a kind of, there's a push and pull here between kind of satisfying the, you want the types, you want the macros, and then you want some types and not others. So it's a tricky problem in practice. I think the only way I can answer to my satisfaction is ensure that for all of the self-tests that things are working well. I think this is one of those problems where the solution is probably not going to be theoretically perfectly clean, but it's hopefully going to be practically useful.
To be honest, I think self-tests will be a little bit too simplistic for like the real tracing application. So I'm not sure, like even if like all the self-tests work really well, like that in practice, this will work really well for like real world applications. But another point, so I think like this macro stuff as a string, right? That's what makes it hard, because it's strings. And it sort of conflicts with the core idea, right? Because core gives you this promise that like whatever you are doing is like relocatable and adjustable across kernels, right? And that's not generally true for macroses, because like when the macro is defined, you compile it, and like if it changes on another kernel, then like you have no way to adjust it. Unless it's like one specific use case where we probably can make it like completely core compatible. It's like when it's integer, right? As you mentioned, like you can do it as a variable or like something like kconfig, and then libpf can adjust that. But like everything else, like even strings are hard, though. Like strings, we can think about this. But like if it's just some random expression, and like what if that expression changes? Like you break the guarantee of the like core relocation stuff, right? So what do you think about that? Like, I wonder if it's actually more dangerous to include such macroses into vmlinux.h, because we give an illusion that like, oh, just use this, and like if something in kernel changes, we will sort of take care of this, and we cannot really.
Yeah, I mean, it's a tricky problem. I think if we're clear about I guess it's one of those things that you might have to just have some caveats around. And if there's guards around all of those macro definitions, people can choose whether they maybe just want the type information, or they just want the macro information, or they want both. So I think if we give people options, that's probably the best we could do. So it's not ideal, but it may be helpful.
Well, look for the Clang. I think the discussion was called weak types, but it's on separate mailing list, on the Clang mailing list. I think like that approach has benefits that, if you are going to use something like some internal definition from the kernel, static inline function, or some pound defined macro expression, right? At least you are sort of aware that you are using something outside of relocatable subset of like vmlinux.h, right? So that gives you a little bit more, well, not you, the user, a little bit more warning, like beware, this might break, right?
Yeah, I think that's important, absolutely.
All right, thanks.
Thanks, Audrey.
Yeah, the guiding principle should be keep it simple at first and add complexity later as needed. Anyone else have any questions for Alan? Alan, thank you very much for your presentation. It's very insightful. It's great seeing people make more progress in introspection and debugging. Thank you very much.
Thanks, David.
Welcome. So now we're going to talk about eBPF and the CPU scheduler for Haru.
Hi, hello. Can you hear me?
Hi there, we can hear you.
Sure. Okay. I'm trying to enable my web camera. Hi, hello.
Hi there.
So do I just begin or wait for time?
Yeah, you can start now.
Hi, everyone. My name is Haolu. I work in Google. Today in this talk, I'm going to talk with my colleague, Barrett to share with some of my experience using eBPF in optimizing CPU scheduling. So in this talk, we will talk about a couple of applications. In particular, on my side, I will talk about 2 applications to do performance profiling for CPU scheduling. One application is to profile the scheduling latencies, and another is to using eBPF to profile the forced idle time in core scheduling. And Barrett will talk about using BPF to accelerate the execution of critical paths in a ghost kernel scheduler. So the first application, profiling the scheduling latencies. So this is a very common use case for BPF to performance profiling when it comes to CPU scheduling. So the common, our application is very similar to the Runco Slower that is in the BCC tool set. So Runco Slower is a tool that to trace the long processor scheduling delays. Our application is slightly different, but the methodology is similar. So we attach a tracing programs to the important scheduling events. For example, like context switch and wake up new. And then in this application, we profile the queuing delays. That's a queuing delay, the time that's spent on waiting in the run queue. In addition to queuing delays, we also profile the on CPU time. That's a time when a thread is using the CPU. That's the time from scheduled on CPU to the time that's scheduled off the CPU. And also profile the off CPU time. That was a time when thread was spent in a sleep state. So this application is a little similar to Runco Slower, but I want to actually highlight 2 differences that we found can be very useful in practical uses. The first is that our applications is C group oriented profiling. But C group profiling is that we provide for threads, but we also aggregate the profiled results by the C groups, the CPU control C groups. By doing so, because in the data center we care on node management, we don't want to care more about is the jobs service level, the jobs performance. The job was modeled as the C groups. And we also break up the queuing delays into 2 parts to give us more insights on the performances. The first part is the wait time. That's when a thread is waiting behind a thread that's from the same C group. And the other is the wait time behind a thread from another C group. This would help us to identify the types of starvations. If it's waiting behind from a thread from the same C group, we know that this is the self-starvation, and the job user could adjust the allocation of the CPU shares within their job. If it's waiting time from a thread from another C group, we know that the users may not have sufficient CPU shares in their job. So in that way, we can advise the users to increase their CPU shares. Another difference is that we don't actually report a single value for the tracing. We profile the stats and report it as distributions in a format of histograms. Within these histograms, we also allow the users for configuration. For example, they can adjust the bucket ranges for the histogram. They can also reset the values to say to do a periodical profiling there. So this application, the profiled results have been used as a service level indicator for node management tools. In Kubernetes, like Kubelet, we have our own internal version, Boglet, in Google. So these are the two differences that I want to highlight in this application. So we also find that using BPF to such a profiling provides benefits. And first, it's very flexible. It's because it's managed by the user space. The user could actually make changes very easily and quickly without involve any kernel changes. And it also minimizes the internal kernel patches we carry in Google. So it's a very nice solution using BPF to this profiling. So the takeaway, so just two differences. One is to the C group-oriented profiling tools and the report distributions instead of a single value for more insights. So far, that's the first part of this or the applications. Is there any questions there? No, I will just move on. Next. The second application is that we're trying to use the eBPF to account the forced idle time. First, I need to introduce some background here. So we have this CPU scheduling feature called the core scheduling. It's a mechanism in the scheduler that mitigates the cross-hyperthread attacks. A cross-hyperthread attack involves the attacker and a victim running on the two hypersiblings of a core, and the attackers could steal confidential information from the victim on the other thread, on another hypersiblings. An example of such attack is our L1TF and MDS. So the core scheduling, the mitigation, it ensures that the threads could be grouped by the user space. So the threads from the same group could share the core. I will have an example in the next slide to show this. And we expect core scheduling to have a better performance compared to the option of disabling the hyperthreading, SMT. So how does the core scheduling works? So before and without core scheduling, we have two threads that's running on two hypersiblings. They can run without interruptions, not interruption. We can run. But if we have a core scheduling enabled, because we can't actually run them simultaneously. So we have the core scheduling will interleave the executions. So this causes a performance issue here, because even untrusted thread is running on a hyperthread, the siblings CPU could either run a task from the same untrusted group or be forced into an idle state. The idle state is a waste of resources here. So that's a forced idle time we want to measure. So why this is important? Because our user in Google in using core scheduling, they want to know that by enabling core scheduling, how much resources efficiency they have lost because of a forced idle. And we also want correct accounting for this wasted resources to the creators of the thread. For example, before, the reported CPU usage for the job is the real CPU usage. But because of a forced idle time, we also want to account the forced idle time to the creator of the thread. So the reported CPU usage will be the real CPU usage plus the forced idle time. So it's also having a forced idle time also is a good indicator for core scheduling the efficiencies, and also help us to understand the mechanism more to give us more opportunity for future optimizations there. But there is currently no upstream solutions on how we measure the forced idle time. There are several things that we need to consider if we are designing a complete upstream solution. For example, what if we have more than two hyperthread siblings? So in order to quickly do some profilings on the forced idle time, we use the eBPF to fulfill such a task. And we find it's a very fast and flexible way. to measure forced out time. And it's also could be using BPF to provide the signals to the user space for future tooling of the scheduling the behavior that our our users in Google really wants, because they have some mechanism in user space by migrating threads to mitigate their loss the efficiency there. So similar to the previous applications, the solution of using BPF to account for cell time is similar. We have a tracing program that's attached to the SCADA context switch trace points and the wake up trace points. Because these attached points are within a core scheduling critical sections, they are protected by the synchronization mechanism for core scheduling. So we really don't have like much concern about the race happening between hyper siblings in the BPF programs. But this has an interesting problem when I developed this application, is that because a forced idle sibling involves knowing the states of two hyperthreads in a core. So this requires us to know what's the sibling run queue is running. So the question is that from within a BPF program, how do we know the sibling hyperthread's current task? So this brings us to an interesting solution we have figured out. So in a BPF program, we can use some mechanism called K symbols. So one could declare a symbol in the BPF program. If the kernel has exported a global symbol of the same name, one could read the exported kernel symbol via the K-Snoop. We have an example in the next slides. So this is a way to access the kernel global variables from within a BPF program. So how do we achieve that? In the user space, the libbpf could read the symbol's kernel address from k-awesomes and fill in that information when we are trying to get the address of that symbols in the BPF program. And the kernel BTF could be used to detect the structure of the symbol. And inside the kernel, the verifiers will do verification to make sure that access to these kernel symbols is safe. Some concrete example here. So we now need to access the run queue of our sibling CPUs. So we can declare the run queues as the K symbols, because in the kernel scheduler, we have the same variable. We have the variable of the same name. It's a static global per CPU variable. So in our BPF programs, we can call a special helper with the BPF per CPU pointer. It's the same, have the same semantic as in the kernel to get the sibling CPU's run queue. And from the run queue, we can detect, we can dereference its current task it's running and the idle task it's Q2 when compared to see if the sibling CPU is idle or not. So the complete algorithm to account for the forced out time is the following. At the context switch time, we take timestamps to indicate that we're entering a forced idle state. There are two conditions. If the sibling CPU is idle and we ourselves are trying to execute a switching to a untrusted task, or we are idle but the sibling is running an untrusted task. And also take timestamp who are exiting this forced idle state. It's the opposite of the state switching. And then we charge the forced out time based on timestamps. With case one, charge the time to the sibling's current task. If it's case two, then we charge it to the time to a current task, or that's the task running our local CPU. So some takeaways here is that using eBPF to implement CPU scheduled stats is a very promising idea. It has several benefits. It's also the ability to be able to read static per CPU variables within BPF seems to be very powerful. It could allow us to pick more kernel states from within the BPF applications. There are many other static per CPU variables used by SCAD, for example, SCAD domains or some others. This could greatly improve the expanded observability of the BPF programs. So this wraps up my 2 applications for performance profiling. Next, I'm going to pass on to my colleague Barrett for applications Ghost.
Hello, can you hear me? Hey, Al, if you get a chance, can you pass the slide control to me or something? If not, I can just say next slide. Hi, everybody. I'm Barrett. I'm going to talk a little bit about Ghost in BPF. Next slide, please. Oh, thanks. I see it.
Barrett, I gave you presenter status.
Got it. Thanks. Okay, so what is Ghost? Ghost is a kernel scheduler class that we've been working on at Google. It sits below CFS in priority. The general idea is that scheduling decisions are made in user space by what we call an agent process. The kernel is going to send messages to the agent, such as task X blocked on CPU 6. And in response, the agent will issue what we call transactions to the kernel, such as run task X on CPU 12. We have a simplified little drawing down here of the rough idea. But so we have inside the kernel, there is a scheduling class, just like CFS or any of the others. And in user space, we've got the process sitting there running decisions. And we also have the ability for the workload itself and the agent to communicate, typically through shared memory or RPCs. And the workload can pass along any scheduling hints. Why are we doing this? Good question. First off, we have a lot of different workloads. So we'd like to have workload-specific scheduling policy. For instance, you can imagine having a different policy for hosting virtual machines versus running a search engine. The other thing that's interesting for us is that agent-to-application interface is independent of the kernel ABI. So we can kind of experiment and do whatever we want between the application and the agent. On a related note, we can update our scheduling policy independently from a kernel rollout. Rolling out the kernel, it takes a little while. It's a lot of difficulties with that. If we want to quickly change a scheduling policy, especially on an application-specific basis, by having this agent be separate from the kernel, we can do that. There's a lot of details about why and how and all that other stuff. And I'll refer you to the recent talk from NetDev. And mostly I want to focus on the BPF stuff. But first I want to dig in a little bit into messages and transactions. These are both through a shared memory interface. Roughly it's shared memory plus a poke of some sort. So from the messages from the kernel to the agent, we basically just drop a message in a ring buffer. And that's kind of what you would expect. The poke aspect to it is that we can also wake an agent on a particular CPU. So, and it doesn't have to be where the event occurred. So we can have, a task X blocked on CPU 6, while the wake up event for the agent could hit on CPU 1, for instance. Similarly, the transactions come from the agent to the kernel. It's not a ring buffer, but there's a per CPU array of what we call ghost transaction structs. And it's got what you would think like the PID for what you want to run, which CPU, and then there's a whole lot of extra little variables that we don't really need to get into, but things you can imagine that you would need to do to keep things synchronized. And the poke for the transaction is a syscall. So the agent can kick the kernel and say, hey, please look at specific transaction requests for particular CPUs. The guts of the transaction really is setting a variable per run queue in the kernel that says, hey, next time we run pick next task ghost, run this particular task. And we call that the latched task. The general idea of messages from kernel to agent, transactions from the agent to the kernel. And there's also various ways we can design our schedulers for multi-core machines. The most basic would be the per CPU scheduler, which is sort of what people are used to these days, where there's an agent task running on each CPU that schedules its CPU only. The one I'm going to talk about more today is the global scheduling model, where we have an agent task that runs on a single CPU, yet schedules all CPUs. You could also imagine various forms of hybrid scheduling, such as a per CPU model sometimes, and you switch to a global model for other things. From the kernel's perspective, there's just an agent task on every CPU, and the user space determines which tasks do what. So whether it's a per CPU model or a global model, the kernel doesn't care. That's actually a policy issue about the agent. Now, of course, you can imagine many issues with the global scheduler. I refer to these as our global scheduling woes. The big issue is that when you picture the global agent loop, well, it's sitting there spinning on a CPU. The typical loop is going to be you handle all your messages, like all the tasks that blocked and preempted and woke up. Then given that information, you say, okay, let's schedule the runnable tasks on all my available CPUs. And then you could do all the fancy policy stuff, like, oh, I know certain tasks are low priority for this application. Let's do some preemptions, or let's try to co-locate tasks that are communicating together adjacent to each other. Now, when you picture a larger machine, that loop can take a while. And of course, it's workload dependent. Like, how many wake-ups per second are you handling? If you have a task or set of tasks that hardly ever wake up, you actually aren't doing a lot in your messaging loop. But if you have a very busy application from a scheduling perspective, then you may have more work to do in your global loops. Similarly, if you have a complicated policy, it might take a while to compute, and then that just adds to your what I call the global loop latency. So for one of our applications, on average, the global loop was taking about 30 to 60 microseconds to complete that handle messages, schedule tasks loop. What this means is that 30 to 60 microseconds is the average amount of time until the agent responds to a message. It's also the average amount of time that a CPU sits idle before the agent schedules it. Now, when you think about that last point, that means every time a task blocks, we're wasting 30 microseconds. Like, that's way too slow. So here's a tool we wrote. It's basically like a BPF-like tool that tells us from the moment a CPU goes idle until a task is latched, meaning that we've had a transaction that says run this task, how long did that take? And you can see here that the bulk of the distribution is in that 30 to 60 plus range. And this is an older one. But that right here, this big bump in the distribution, that's the global agent's loop time. And that's how much time we're wasting every time we block, which is pretty bad. So let's use BPF so that we can respond quickly to these events. So we have a bunch of options. When we do pick next task ghost and we have no latch task, well, our options are, well, we can idle and then just wait for the global agent to notice. That's the 30 to 60 microsecond wait. No thanks. Another option is we can wake that CPU's agent, because remember, every CPU has an agent task. And we can wake that agent, then that can issue a transaction. Well, that's extra context switches. How about we run a BPF program? That also can issue a transaction. So we have a type, I refer to it as BPF PNT for a pick next task. It's a special prog type that we've made. And it attaches at one point in pick next task ghost. And what it can do is latch tasks. It can also wake agents. So we have a couple helpers to do this. There's the ghost wake agent helper, which is essentially the kick the agent on a particular CPU. And we have the ghost run task, where this is basically what a transaction is, where we say, on this CPU, I want you to run a particular task. This lets BPF do mostly whatever the agent can do. I want to emphasize that these BPF programs are part of the agent. They're extremely coupled to the agent. So they're embedded in the binary, like libbpf with the BPF skeleton. These programs have the same lifetime as the agent. Specifically, the agent holds the FD open from BPF link create. They're also coded side by side, for instance. So when our EDF schedulers, C code, and the BPF code basically have them open in the same window. It's like you're programming in shared memory. And they are specifically sharing memory with the agents. I use a BPF array map, and user space M maps it. So I tend to think of these BPF programs as just a thread that happens to be running in the kernel. And then half jokingly, I call this ring B, analogous to ring 3, where we have the array maps are really windows into the agent's address space. And if you want to keep pushing on the analogy, those BPF helpers, like they wake the agent and run the ghost thread, those are kind of the entry points to the kernel, like syscalls. And if we really want to go even farther, we can say that BPF prog run is sort of like the interrupt descriptor table vectors. But the main point is that these aren't independent programs. This BPF program is the agent. It just happens to be in BPF instead of in Ring 3.
Barrett, I believe Vladimir has a question. He raised his hand.
Sure.
Vladimir.
Go ahead, please.
Yeah, go ahead if you have a question, please. Okay, I'll take that as not available or something like that, or miss button press. We can do Q&A later.
That's great.
Please continue.
Thanks. So let me talk about, I have an example BPF scheduler that we made that runs with a global agent, where the agent in Ring 3 is pushing runnable tasks into yet another ring buffer. And the BPF PNT program consumes these tasks. So when PicNextTaskGhost comes, it will look and try to grab a task from a ring buffer. And I want to emphasize that this isn't any ABI with the kernel. This is purely between Ring 3 and Ring B, if you will. We actually have a hierarchy of ring buffers, and you can do this based on the cache hierarchy. So you have like per CPU rings and then per NUMA rings. You can actually do whatever you would like, but this is just one version of this that I have for one of our global agents. And once the global agent pushes those tasks into the rings, it can actually monitor them to see did any of the CPUs pick this task up. What can I do? Well, then the agent can say, let's move a task from a CPU ring to a NUMA ring, or maybe just load balance in between CPUs. The idea here is that BPF PNT is sort of the mechanism that is gobbling tasks up from these rings and running them as it can. And then the global agent is more detached, handling the bigger picture stuff like load balancing, or for instance, if we can have a higher priority task that didn't run in a certain amount of time. Well, in that case, the global agent can still issue transactions to preempt some other task to basically handle more one-off events instead of just like the common fast path that we have the BPF PNT handling. And the agent you can come up with whatever program you want. It's all independent of the kernel. It's in the same idea that why we have user space ghost in the first place, of like the policies in user space, you can do this independently of the kernel. Well, now you just have these BPF hooks too that you can do. Just as an example, you could, we don't have this, but if there's a map type for a priority queue, you could do something like that and have per CPU run queues. It's completely independent of the kernel hooks that we've got. Once I've added the global scheduling with BPF PNT, you can see the idle to latched times. The bulk of the time is now when BPF PicNextTask finds a task to run that the agent has pushed in. However, we still have a little bump here around the the 16 to 120 microsecond mark. That's still the global agent loop. It's possible that the agent falls behind handling messages and doesn't have enough runnable tasks to keep the BPF PNT threads busy. Well, what can we do about that? Let's maybe talk about wake-ups. So right now we have BPF at PicNextTask, but it's not enough to only run there. We want to be able to respond quickly to thread wake-ups and other runnability edges, such as yields, or more specifically, CFS runs at a higher priority than Ghost. So when CFS will preempt us and then return the CPU to Ghost, that's another event when a thread becomes runnable. Well, either way, it's a runnability edge, if you will. And what we want to do is keep BPF PNT busy with tasks to run. Now, if we go back a few slides, if you recall messages, those are the primary mechanism from the kernel to inform the agent of any sort of ghost event. We got things like, thread woke up, thread blocked, thread was preempted. Now let's see, thread new, affinity change, departed, stuff like that. There's a lot of them. Now, BPF is part of the agent. Let's interpose on the message delivery itself. So I have a BPF message type BPF program, and the context itself is a struct BPF ghost message. We attach it at a specific point in the ghost kernel code, which is the one spot where we send all messages to because of a task. And Basically, that gives BPF the opportunity to respond to messages even faster than the agent's Ring 3 code would. It's still the agent, it's just running in BPF instead of in Ring 3. Now, one question you may have is, earlier I mentioned that messaging was yet another ring buffer. Could we replace ghost messaging with the ring buff? I certainly think we could. They're both shared memory ring buffers, power of 2, all that stuff. One minor thing for us, at least, is that all agents would need to use BPF, which so far we only have a couple of them that are using it. The thing I do like about it is that it would allow agent-specific customizations to those message payloads. Because right now, the format of the ghost thread runnable message, for instance, is part of our ghost ABI. That would be the ABI to talk to BPF, but you could imagine an agent saying, you know what, throw in a couple extra bytes of data into a payload and send it to Ring 3. But yeah, that's sort of where we're going with the wake up stuff. When you think about it, do we actually even need a user space agent? If BPF is part of the agent, maybe we don't need one. And from my perspective, it's actually all the same agent program. And the kernel, the ghost kernel code is talking to the agent through messages. It doesn't matter if it's Ring 3 or Ring B in my head. Either way, I sort of have a set of things I want to be able to do to enforce policy, like run task X on CPU 3, or maybe just set need reschedule on a CPU, kick somebody off a CPU, or what we don't do yet, but we think about doing would be to say, hey, let me control what level of C state sleeping we want to go into. So whether we have a user space program or a BPF program that does it, don't really care as much. And either way you do it, I think the Ghost kernel code already solves many of these problems that you would have, whether it's BPF or purely BPF or purely user space.
I guess this is a good question about what is the traditional design principle, keep policy out of the kernel, really mean when we have BPF involved?
Yeah, it's a good question. I view the BPF hooks, at least the ones that we've got, as the mechanism, but the policy itself is the brain that was loaded from user space, whether that was Ring 3 or Ring B. But one of the cool things we've mostly sorted out is the problems of delegating scheduling to an untrusted agent. And like, what are the messages, like the specific messages, and what are their semantics and some of the parameters? Just as an example, I counted the number of places from which we send message task new. We have 5 of them currently, and a lot of them are just weird corner cases of, someone calls set sched on a task. What do you do with fork? There's a lot of little messy corners. One other aspect to this is that it is easier to code in user space than in BPF. For instance, we do like to communicate with our applications. So we have easy access to RPCs. You can spin forever in the global agent if you want. There's a lot of little stuff. You don't have to battle the verifier. That's a fun one. But yeah, I think even if I had an agent that was primarily BPF, I'd probably want a user space component just to make life a little easier. Anyway, this is just a little bit about Ghost and BPF. The main ideas behind Ghost is that we delegate kernel scheduling to some form of agent process, and that process is made of both user space and BPF components. And BPF is mostly used by us as an accelerator to recover some of these overheads of going out and back to user space. Because Ghost basically is going to user space isn't free, and there are trade-offs with the design, and BPF sort of helps us recover some of those trade-offs. There's a lot more about this stuff, and I glossed over pretty much everything that's not related to BPF. So if you want to check out some links, there's our NetDev talk. There's a paper coming out in SOSP in I think about a month or so. We also have a few links to our code and user space. That's it is a little behind. It does have BPF picnic stats if you're curious, but it doesn't have that message stuff, which, to be honest, I did that last week. So anyway, I'd like to take any questions.
All right, Barry, thanks a lot. So if we have any questions, please give them now. I guess this is an interesting general problem of putting a important kernel policy decision into a user space agent of some point. I mean, the traditional example would be like a routing daemon where we define the API for changing routes and then the user space process deals with all that stuff.
Mm-hmm.
Or OVS user space would maybe be another example. And here we're putting the guts of the process scheduler into a user space process as well, but using BPF as the mechanism for defining an interface to do this safely, which I think is an important component of all this work.
Yeah, I didn't talk too much about it, but we have a bunch of safety things all in the kernel itself. So like you can only latch tasks under certain circumstances. Like if a task, for instance, is already running on a CPU and you try to latch it somewhere else, that you'll get an error response that says, "Hey, this one's busy," and stuff like that. The other thing is that if the agent, whether BPF or user space, fails to schedule a task for a certain amount of time, we've got little kernel watchdogs that'll say, and this is configurable by user space when this kicks in. But if we, for instance, it's very easy to have an agent deadlock itself just because you're developing these things. The kernel will notice that and basically destroy the agent and kick all of our tasks back to CFS. So that the general point being that Ghost shouldn't be able to permanently harm the system in any way. You might have commands and issues.
That's good. I was curious how you would handle the case where no response happened to requests to deal with the task.
Yeah, and from our perspective, we want to run this to get better performance out of it. But if things are turning out poorly for whatever reason, like our Borg, whatever the daemon that watches all of our nodes, it can come along and kill the agent if it wants. There's lots of reasons. It's very easy to kill an agent, if you will, so that we can restore the system to same performance.
So if the agent dies, everything goes to CFS.
Yeah. And we also have ways in which we can live update, if you will, from handoff from one agent to another relatively quickly. Like it's a larger topic, but the general idea is that most of the kernel state, most of the important state is in the kernel. Like so, if the agent dies and a new agent comes back up, it is possible to reattach to the previous Ghost Sched class. The state of all threads is in the kernel, and user space can ask for it at any time. So a new agent could come along and say, which tasks were there in Ghost? Let me quickly, and if you can establish it quickly enough, then the kernel won't kick you back to CFS right away. So there's this little timeout window.
I see.
But yeah, there's a lot of stuff like that we talk a little bit more about in some of our other stuff. But happy to answer questions about that too. That's
cool. Anyone have any questions? Here's your opportunity to ask about this.
Oh, hello. Excellent talk. I was wondering, what are your plans to upstream the kernel changes?
So we have them upstream for the most part now, but the GitHub stuff lags behind a little bit. So we do most of our development on our internal Google kernel, mostly because the stuff we're testing it on requires that. But we do backport the things to or forward port, I guess. But we port them to the users to the repos there relatively frequently. But it doesn't have the absolute latest stuff. So I have that disclaimer there. As far as getting it into the upstream kernel itself versus just being open source, that's a good question. I think we certainly would like that, but whether upstream would like that, that's a different discussion. I think there's a few things we want to sort out too about like our interface changes frequently. We're on version, I think, like 46 of our user API. So we would want to have solidified that before proposing it for upstream.
Okay, Barry, thank you very much.
Cool, thanks.
So I forgot to do a break last time, so we're going to have a 20-minute break now. So come back at like 8:33, I guess, Pacific time. All right. So we'll come back at 8:40 to do the next presentation. Meanwhile, get yourself a tasty beverage. We're just going downstairs again. You've been here many times. Your food's down here too. Don't scratch up this shirt, okay? Aw. The struggle is real. Hmm. What's up? Yeah. 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 You want to go, don't you? Okay. No more torture. Go. No one comes back. I'll just sit here drinking beer, okay? What does it mean to abstain from a question like, are you ready? Abstain. I guess some people just don't know if they're ready or not. I'm ready. I know it's okay, abstain. You're just messing with me.
Well, you kind of asked for it, didn't you?
Yeah, right. It's just like staring at you like, if I want to be antisocial, I could just press this button. It's so easy.
I mean, the real question is what happens if you vote no? Do you get another chance to vote?
Right? It doesn't let me vote at all, which is kind of like disappointing. Like they didn't think that through. Like maybe the person like giving this the poll would like to voice their opinion as well. Honestly, I would abstain too. I would want to be that guy. I have these Google Nest cameras, one in the backyard and one in the front door. So every time my neighbor goes to take some garbage out, I get a notification on my phone. I'm like, I don't need this right now.
So this could be the break entertainment.
Right.
So is the chat working yet?
It looks like it's just not really working.
Yeah, I can chat with Jesper because we're on the same matrix server.
I see. Lucky you guys.
But I don't think anyone else can see it. Oh, well.
Nope. You Danes can just go chat all you want.
We'll just chat with ourselves. I can see there's 188 other people's joined, but I don't know if they can see my chat.
Right. I don't see it. I tried to send testing in there. It never goes. It just goes into dev null or something. It went into a ghost scheduling queue, and I'm waiting for the agent to time out. Jesper, what do you think? You're fired, man. I don't need you to like illegally export coffee collector beans anymore.
Oh, that's true. You can buy them in London, right?
Right.
I managed to join the chat in another window, like in the official channel, and now I saw my own message pop up, but it took a while.
Oh.
But the chat, I cannot join it from the integrated stuff.
Yeah, I can't either. It just spins endlessly.
Yeah, I joined it with the link I think Daniel sent in the chat, in the shared notes.
So this is the great thing about distributed systems, right? They fail in such interesting ways.
And as a service message for people trying to join the chat, when you log in on the link that's in the shared notes, it has to be your email address, but without the at sign. So you have to replace the at sign with a dot as your login name.
If you hadn't told me that, I would never figure that out.
Yeah, it's in the official documentation for LPC.
Nobody reads documentation.
It was also at the very end of the long email, so I guess no one reads that either.
That's not qualifying for official documentation. Now that login is spinning for me endlessly. Come on, log me in. Jesper said it was in the official documentation. It should work. At least I don't have to log into a Matrix server to drink my beer, right?
You don't have to, but maybe it helps.
Helps in what way? I don't get it. Is that some Danish joke? I don't understand. I am trying. It's just not working. It says setting up keys now. That's scary.
So presumably this is the thing that falls down when thousands of people do it at the same time.
Something like that. So 10 more minutes and we'll get going again.
Hey, I'm the 3%.
So let's try this again now that we have 10 minutes left. Okay, hit the abstain button. I see you did it already. Wow.
That wasn't me this time.
Someone else. Everyone wants to be cool like Toke.
Now I don't know what to do.
You have to, there's no other way to be different than to try to be different just like everyone else.
We are all individuals.
Yeah, exactly. That's the quote. Eat some chips. Drinking beer, I'm eating salty potato chips. The name of this presentation is David Wants to Have a Stroke Again. I guess that's not funny. So let's get the slides up. Whenever Kuniyuki's ready, we can start his presentation. Hello, Kuniyuki. How are you doing?
Hi, I'm doing well.
Good.
Okay.
Maybe wait like a couple more minutes and you can start.
Okay.
Where are you located?
Oh, I'm in Japan.
What time is it in Japan right now?
0 o'clock.
It's like midnight. Wow.
Yeah, midnight.
The sacrifices we make to attend conferences virtually, right? Sorry we had to keep you up so late.
Yeah, no problem.
You'd probably be reading code at this hour anyways. No comment.
You should do another poll of how many kernel hackers are actually nocturnal.
Right. That would be a good poll, right?
Your message did get through to the chat.
Yeah,
I also
saw it
responded,
too.
but I can see there's some delay because I have two accounts logged in, so I can see it. I haven't seen my
And
own
one of them is
message
typing right now.
yet. Yeah.
Oh my god. Finally got into the room and I could say hi.
Hey, I got your high.
Good.
But there's some delay, right?
Yeah, it takes a while. It took me like 5 minutes to join the group. Welcome to modern technology, right? All right, Kuniyuki-san, whenever you're ready, you can start.
Okay. Okay, let's start. Hi, everyone. Thank you for joining today. I'm Kuniyuki, Cloud Support Engineer in AWS. In this session, I will talk about some improvements for SRE support available in the 5.14 kernel. First, what is SRE support, and when and where it misbehaves, and finally, how to make it acceptable. What is SRE support? SRE support is a networking SCADA option added in the 3.9 kernel to implement high-performance servers, and it can replace the traditional approaches used in the prior version of the kernel. Without SRE support, only one SCADA is allowed to listen on a given TCP port. So if another SCADA is listening on the port, bind or listen system call to the same port failed with the ELS in user. This Python script tried to create two server SCAD by calling SCAD bind and listen, syscall twice for each, and the scan bind paired with the error. To build the high-performance servers and this constraint, two traditional approaches were often used before the 3.9 kernel. The first is to have a single data process that accepts connections from a listening SCAD and distributes them to other worker processes. And the SCADA is to share listening SCAD within multiple worker processes, and they call the accept syscall to the same listening SCAD. However, both approaches have problems and high load. With the first approach, the accept syscall and distribution of connections can be bottleneck. And also, with the SCADA approach, the accept syscall can be bottleneck. Connections from clients are put into the listener's accept queue, and queue is protected by spin lock. So the lock is contended by multiple accept syscalls. And such a contention can occur when the kernel put connections into the accept queue. So due to the accept bottleneck, this approach does not scale well on multiple systems. In addition to that, the second approach has another problem. With the first approach, the user can implement logic to balance the connection across the worker processes. But with the second approach, each process waiting the accept system call, but the wake up is not fair. So the connections can be distributed unevenly. To address these problems, the SRE support option is introduced. It allows multiple SCAD to listen on the same port. This script tries to create two server SCAD as well, and it succeeds because all SCADs have SRE support enabled. With this option, each process can have its own listening SCAD and accept connection from it. So the bottleneck is addressed in this way. Also, when the kernel puts a connection into an accept queue, it selects a listener randomly, so connections are distributed almost evenly. In this way, the SRE support option addresses two problems. But as we can see from the initial merge commit that introduced SRE support, the TCP implementation has a problem. Okay, then let's take a look at when SRE support misbehaves through two quizzes. Quiz 1. What do you expect to show up in your console when you run this script? First, server 1 listens to the 80 port of the local host. And clients connect to the 80 port of the local host. At this time, only server 1 is listening on the port, so the connection is added into server 1's accept queue. And server 2 starts to listen on the same port. Then we close the server 1 here. Note that the connection from the client has not been accepted and server 2 is still listening in the port. Finally, we make the server 2 non-blocking and call accept and receive system calls. Then, what do you expect to show up in the console? Of course, we want to see hello world, but unfortunately, we cannot see it. Instead, we will see the resource temporarily unavailable. And that means this is E again, and that means there is no connection in the accept queue. So when we call accept system call, the server 2 did not have any connection in its queue. Then, where is the connection from the client and what happened to it? If you run TCP dump, you can see a reset packet is sent out from the server side, and the connection is aborted. So there is a problem that even if server 2 listens on the same port, when we close server 1, the connection is in the server 1's accept queue are lost. This kind of situation happens when we load server processes. As we can see from case 1, when we close the listening skid, the connection in the accept queue are also lost. To avoid this problem, we have to do connection draining before closing the listener. Connection draining is to call the accept scheduler repeatedly until we see the E again one. And it is step 2 and step 3 in the diagram. E again means there are no connections in the accept queue, so if we confirm the error, we can close the listener without aborting connections in accept queue. But SRE Pro still has another program. Let's move on to the next quiz. Quiz 2. Again, what do you expect to show up in your console when you run the script? First, the server 1 listens to the 80 port of the local host. And the next is different from quiz 1. The dropback as an IP tables loop that drops packets only with the ACK flag. Then, client connect to the 80 port of the local host. But the ACK packet is dropped and the three-way handshake does not complete at the server side. Such a connection cannot be accepted, so the connection has not been put into the accept queue yet. Next, server 2 starts to listen the same port. Then we close the server 1. Here, both accept queues are empty at this time. And then we remove the loop and wait 1 second so the same ACK or ACK is retransmitted. And finally, we make the server 2 non-blocking and call accept and receive syscalls. Which message do you expect to show up? Hello world or E again? This time, also we will see the E again message. That means server 2's accept queue was empty, but server 1's queue was also empty before closing it. Then, where is the connection and what happened to it? If you run TCP down, you will see a reset packet again from the server side. So there is another problem that even if server 2 listens the same port, when server 1 is closed, then connections that are not in the accept queue are lost. This situation also happens when we reload server processes. And the difference between the quiz 1 is that before closing the listener, there is in-flight request that does not complete three-way handshake. In this case, connection draining does not work. The implied request during the handshake is not in the accept queue, so we cannot know the existence by the accept scheduler. But as we can see from quiz 2, the implied request actually seems to be tied to a specific listener. And if we clone the listener, the request is aborted. That even if we confirm the E again alert, When we close the listener, invisible connections can be lost silently. There are two major workarounds for this issue. The first one is FD passing. We can pass 5 descriptors through Unix domain scat with the CMWrite type of message. In this case, we need not close listeners, so the problem does not happen. Also, this approach does not need connection draining, so that we can apply the new server settings faster. But it has a downside. With FD passing, it is not easy to scale out or scale in servers. One of the merits of SRE support is that each process can work independently. That means the new listener need not interact with the old process to listen the same port. That characteristic makes it easier to scale out or scale in servers by simply adding or removing processes. But FD passing needs interaction between processes and loses this merit. And FD passing need not close the listener, but it means it cannot close the listener. If we want to scale in servers, even then we have to pass the listener. Otherwise, connection failure happens. So if we do scaling out, scaling in, and scaling out servers, we will see that the first and scan scaling out require different operations. For the first time, the process creates a new listener, but the scan time, the new process has to receive a listener from another process. And if configuration change happens and the new process listens on another port, the old process cannot pass its listener, and it will have to close it. Then the problem happens, and we cannot avoid service disruption in such a case. So if we use FD passing, we have to accept this kind of complexity. And another workaround is connection draining, but it uses a BPF feature added for SLE support and the 4.19 kernel. The we use protocol is a BPF map to which we can add listeners on the same port. And the new type of program is executed when the same packet is received. By calling BPF SK select release port and returning SK pass, we can decide which listener in the map processes each connection based on its packet data. The struct SK release port MD is passed to the BPF program, and it contains packet data, packet length, protocol, and etc. So with this feature, we can avoid such connection failure in the following steps. First, add a new listener to the map, and then remove the old listener from the map. This stops routing new connections to the old listener. And wait for CNAC timer to expire. This will release 31 scans by default. Then we can ensure that all in-flight requests complete through a handshake, and they are put into the accept queue. Then we can do connection draining to block connections out of the accept queue. In this way, we can confirm that there are no connections tied to the listener. And finally, we can close it safely. With this workaround, each process can work independently, so we can easily scale several processes, and the user space logic will be simpler. But with connection draining, the processes with old settings remain longer, so it might not be desirable in terms of security. For now, we know there are two workarounds for the problem, but they are workarounds and not genuine solutions. The behavior that closing the listener avoids some connections is reasonable if only one schedule is listening on the port. The kernel should avoid the remaining connection then, so in that case, such connection failures are acceptable. But what if other schedulers are listening on the port? Why isn't other schedulers unable to accept such connections? So let's see how SRE support is implemented and where it misbehaves. To implement SRE support, we have to handle multiple schedulers on the same port and distribute connections. The SCAD bind and listen chess goals seem to work well, but on quiz 1 and 2, the three-way handshake and the cross syscall seem to have problems. So let's take a look into 2 parts. First, the three-way handshake, and when the kernel receives a packet, it looks up a proper SCAD that can process it. Basically, the SCAD lookup consists of 3 lookups for the 2 hash tables. The first lookup is done in a hash that contains no listener that matches 4 tuples of the packet. But this time, no proper SCAD is found. Then, the scanner lookup is done in hash 2 for listener that matches 2 tuples. And if no listener is found, the final lookup is done for hash 2 with 1 tuple. If resolution port isn't enabled, then multiple SCAD may listen on the same port. So if the kernel selects the first found listener in the hash list to process connections, it cannot balance the load. So for load balancing, the kernel must randomly select 1 listener on the port. For this listen, when a listener is found for the first time, the kernel stops traversing the list and do 1 more lookup. Another lookup uses Structs subgroup port, and it is allocated to a listener when a SCAD is found to a port with SRE port enabled, and it is shared within the listeners on the same port as SKRs for CB, and it contains references to all of them in the LA socks. So if the kernel finds even 1 listener in the hash 2, it calls the response select sock that picks out 1 listener from the same response group. By default, the kernel selects a listener randomly to distribute connections evenly, but it can be controlled by BPF. Yes, this is a feature used in the workaround for the quiz 2. And once a listener is found, the kernel plays a small size SCAD that represents a connection request. This is kind of simplified mitigation to avoid allocating much memory for suspicious packets that might not complete the handshake. At this time, the main SCAD is typed to a listener through the LSK listener. Then, the kernel puts the main SCAD into a hash so that the next packet is processed based on the lookup SCAD. And then the kernel sets a sync timer. And finally, it sends a sync packet. And when the final act of the handshake is received, the kernel will find the main SCAD in the hash. Then, from the associated listener, the kernel clones a full-size SCAD Structs sock, and the kernel links it to the main SCAD as SK. Next, the kernel swaps the mini and full SCAD in the hash so that the packets after the handshake are processed based on the full SCAD. Then, the SCAD transitions to the established state. And then, the kernel removes the sync timer. Finally, the kernel puts the new SCAD into the accept queue and finishes the handshake. At this time, the full SCAD is acceptable, and the main SCAD is only accessed from the accept queue. And there is another handshake done, TCP fast open. If a same packet has a TCP fast open cookie and it is valid, all the previous steps are done at once before sending SYNAC. So even if it is an in-flight request, it can be accepted if it has a valid fast open cookie. So each socket is linked like this. We can see there are 2 types of connection, that is acceptable one and unacceptable one. The acceptable connection includes the established connections and in-flight request with TCP fast open cookie. And the unacceptable connection includes the standard in-flight request. The important difference here is that the acceptable connection can be referred from the listener, and the unacceptable connection cannot be referred from listener. That means the acceptable connection can be freed during the closed syscall, and the unacceptable connection cannot be freed at that time. So they are freed after the closed system call. Okay, let's see where each connection is aborted. First, the closest goal calls resport the task log, and it sets new to SK resport CB. Then it moves the last socket in the resport group into the closing listeners position, so that the kernel never selects the listener for new connection. Then it decrements the number of listeners. Next, the kernel will remove the listener from the hash2, and then it changes the listener state to TCP close. And it calls INSGSK listen stop. This function frees the mini and the first get in the accept queue one by one. So request get queue remove pops out the mini get, and INS try get remove the first get from the hash and does some free now. And then request get put free the mini get, and finally suck put free the first get. This way, acceptable connections are aborted one by one during the closed system call. After the closed system call, unacceptable connections are freed up. An acceptable connection can be referred only from the eHash or its SYNAC timer. So it is aborted when receiving the final ARC packet or retransmitting a SYNAC packet. When receiving the ARC packet, the kernel looks at the miniskit and checks its state. Then the kernel checks if the listener state is TCP listen or not. If the listener has been closed, INSGSK draw benefit is called, and it removes the miniskit from the eHash and removes the SYNAC timer, and then leaves the miniskit. Okay, and when the kernel transmitting a SYNAC packet, it calls the request get timer handler. That gets the miniskit from the timer, and then it checks the listener state as well. And finally, it calls same function and frees the miniskit. As we have seen so far, SO resport works along the scat layer, and when selecting a listener, and other behavior the same with no resport case. This makes the implementation simple. So if you know this, you might think the connection failure is reasonable, but it is still unacceptable. Then how can we make it acceptable? The connections are aborted in the three functions. If the SCAD has SO resport enabled, we should check if another SCAD is waiting on the port. And then if it exists, we should be able to migrate the mini and first SCAD from the closing listener to another. The resport group contains our listeners, so we can look up another listener in the resport group. But to look it up from the closing listener, I added some changes regarding these two functions. So resport detach sub removes the listener from the resport group and set new to SK resport CB, and it is called just after close. So the resport group cannot be accessed in all the connection failure paths. But luckily, it is also calling SK destruct. That frees a listener. A listener is not freed until all of its miniskets are freed. So if we do not set no in the first call, and we can access the resport group from the closed listener in no connection failure path. But it is not enough because of the resport rule. Resport rule is called when the number of listeners on the port overflows the current limit. Then it allocates a double-sized resport group and redirects all listeners SK resport CB. So the closed listeners SK resport CB can be stable. To avoid this, we have to keep the closed listener in the resport group even after closed system call, so that resport group can redirect the closed listeners SK resport CB. So I added a new function and replaced it with the first resport detach call subcall. It does not set new to SK resport CB, and it moves the closed socket backwards in the resport LA to be copied by resport load. With this change, the kernel can look at the resport group from the closed listener when connection failure happens. And to work it up, I added resport migrate sock, which looks almost the same as resport flex sock. And it is called while and after closing the listener to select a new listener. By default, it selects a new listener randomly, but it can also be controlled by BPF. And once another listener is found, we can migrate socket. In the first implementation, I reload the LSK listener directory to the new listener, but it is not safe in the unacceptable connection cases because another CPU may be referring to the minisked. For example, two CPUs might read LSK listener simultaneously, and one CPU can see an inconsistent value. So changing LSK listener has not been expected so far, and it is unsafe. This was pointed out by Martin Kvailov at Facebook, and he gave me a good idea. So directly writing LSK listener is not safe, so we have decided to clone the minisked and write the clone the one's LSK listener. Then we put it into the accept queue or the e-hash based on the connection types. So before migration, it will look like this. And first we look up a new listener by the resport migrate sock and clone the minisked. Then link it with the e-hash and the accept queue for each. And finally, we can create the original minisked, and migration completes in this way. Okay, then let's see how it works with the scripts in the quiz 1 and quiz 2. Okay, quiz 1 looks good. We can see hello world message, which was lost before. And quiz 2, we can see the truly expected message as well. But you might wonder why the scatter migration feature is controlled by sysctl and it is disabled by default. So this is because there may be listeners with different settings at the set socket level. Let's say two servers listen to the same port and only the new server is configured with the TCP save SYN option. If the option is enabled, the kernel saves SYN packet data to its socket. And after accepting the connection, we can retrieve the data by the get socket syscall. And what if scatter migration happens from the old server to the one? In the new server's accept queue, there are two kinds of connections, and we can get the same packet data from the new server's connection, but we cannot get it from the old server's connection. So if the listener on the same port have different settings, scatter migration might break the application. And also, a BPF program might be attached to the listeners to define the routing policy for each connection. The kernel migrates get randomly by default, but this is not desirable in this case. So the migration feature is disabled by default for safe. For such cases, I extended the existing BPF feature for SL export with a new attach type. If the attach type is a new one, the BPF program is executed when a SYN packet is received and when the connection is migrated. This makes it possible to select a proper listener in the cases before. And when selecting a listener, we can know for which connection and from which listener the migration is happening. The SK is the resport MD. The SK in the resport MD is the closed listener. And the migrating SK can be a minisked or full sked, depending on the connection type. If it is an acceptable connection, then the migrated SK is full SK, and it is an unacceptable connection. Migrating SK is a mini SK. So if you have different listeners on the port or attach a BPF program, then you can use the new BPF attach type. Otherwise, just turn on the syscontrol node. This is the final slide. Conclusion. So closing the listener avoids two kinds of connections, acceptable and unacceptable connections. And the SCED migration feature is available from the 5.14 kernel, and it prevents such connection failures when other listeners exist on the same port. And it makes hot loading easier and faster. Thank you.
Okay, if anyone has questions, now's the time to do that. Any questions, anyone?
I have a question here. So thank you first of all for this presentation. My question here, when you talk about SO reuse port, how is it different from SO reuse address?
Sorry, could you say again?
Yeah, I can't hear if you couldn't hear me. So basically, I believe there is another like TCP option which is called SO reuse address. How is it different from SO reuse port?
No, SO reuse address does not allow multiple listeners on the same port. So SO reuse port can allow it.
So this is the only difference?
And SO reuse address makes it faster to reuse the port. So you can so for such a use case, you can enable the SO reuse address and SO reuse port at the same time.
Okay, makes sense. Thank you.
Yeah, thank you.
Any other questions? If there are no other questions, then we'll break till 9:30. Kuniyuki, thank you very much for your presentation.
Thank you.
Okay, we'll start up again at 9:30 with Yuri's presentation. Okay. No, halfway through. We're at break time.
Forgot the what?
The screen is on.
For what?
The camera's on in case you want to put it on my laptop.
Oh yeah, that's nice. Did she say hi
She meowed earlier.
the first time?
The second time, yeah.
I see.
Affogato. Not interested, huh?
You muted?
No. Say hi. She's gonna run away before she says hi. Bye bye. See ya. Jerry, I made you the presenter, so at exactly 9:30, why don't you just get started, okay?
Right. Okay, sure.
Cool.
Okay, hello everybody. I hope you can hear me. My name is Iri Olsha. I work for Red Hat. This presentation is about mass attachment of tracing points, tracing probes. Basically, it's about adding another batch API to the BPF and the batch API for attaching the tracing probes, the trampolines. This is actually still ongoing work. There were 2 versions of the patch set already posted, and I'm working on another one. So there was already a bit of reviews. We changed the interfaces, and this presentation is about to give the current status on what's actually already been merged, because there's one thing that already got merged, and what is the current plan for the next version. So actually, what is the problem we are trying to solve? What's wrong? The wrong is the attachment time if you want to attach multiple trampolines at a single time. So for example, if you run tools like BPF trace and you specify kfunc, which is actually the FN3 trampoline, and do the wildcard, and this wildcard actually resolve in like thousands of the functions, it can take really like several minutes before the actual trace can start, because the attachment itself of those trampolines takes really long time. It's actually the problem of the interface. It's the problem in the kernel. If you run any other tool like K-Snoop or any other tool that wants to attach really many trampolines, you will hit the issue. What I'm actually talking about when I'm saying attachment of the trampolines, so every function that you want to attach, like in this example with the BPF trace, each of the functions has no operation instruction at the beginning of the functions, and when you attach the trampoline, you basically the kernel overrides the first instructions to the call to the trampoline, and the trampoline itself is calling the BPF program. So this is like the core operation of the attachment. So basically, writing in the running kernel, overwriting the NOP instruction to call to the trampoline. This attachment itself, this core operation of overwriting the NOP to the core trampoline, is actually not done by BPF subsystem. There is attach layer for that, and there are actually 2 of them. Currently, BPF can use the ftrace direct entries API or textbook BP function. The difference is if you have ftrace enabled on your kernel, and the chances are that you have, ftrace is actually keeping record of every traceable function in the system. So if you want to add another attachment like BPF attachment through the ftrace, we need to go through the ftrace API. So that's one attach layer. If, for example, the function is not being traceable by ftrace, but it's still available, or if you don't have ftrace enabled, then we can use the BPF is using the textbook BP function. Anyway, both of them are dependent on ftrace setup, so kernel needs to be compiled with that PG and MFN3 options to to have this no operation instructions at the beginning of each functions to have this space. And also, I mean, this no operation instruction is put there by the ftrace on the startup, so that needs to be done for both of them. All related work that we did is actually in accordance with the ftrace, because we want BPF and ftrace to live happily on the same system. So that's the attach layer, the ftrace direct entries API that we considering when we are using when we are attaching the trump line. The current API for the attaching is this easy. There are 3 functions: register, unregister, and modify. You basically get the function IP address and the address of the trump line on the input of the function, and the register will actually make that attachment happen. It will make that call at the beginning of the function and register this change in the ftrace subsystem. Same for unregister and modify. You can disable the change, or you can change the call to another trump line. So currently, how it looks like what are the operations when you want to attach the trump line is that you load the program, and then you call the Bpf syscall raw trace point open command on that program, and it will do all the work. It will end up with generating the trump line for the function. So it will have the address of the trump line, and it will call the register ftrace direct to actually attach the trump line to the function. So it will do all the necessary thing in the ftrace, and to get it, also it will run some RCU sync timeouts. And this is basically the source of the delay. So currently, if you do the attachment of multiple trump lines, you end up repeating these 2 syscalls for 1,000 times, 2,000 times, depends how many functions you want to open. And this registration in the ftrace together with this RCU sync timeouts is source of the delay. So after some discussion with Steven, we also asked if it would be possible maybe to keep this interface and to decrease those synchronization timeouts. It might be possible, but still there would be some. So we decided that the way is to add new batch API that would actually make the attachment for multiple functions in one syscall. So how does it actually look? So yeah, we are adding the new batch attach API that can attach all functions in one call, and that interface has actually BPF part and the new ftrace API part. Let's start with the BPF. So at the moment, as I said, there were 2 patch sets already posted. So this is so far how the interface looks like. It's quite easy. You load the program with the new flag BPFF multifunc, which actually informs the verifier that this is program that can be called from multiple functions. And we created the new type of link called tracing multi, which expects on the input on the link crate structure the array of BTF IDs, and each function is represented by BTF ID. So the user just specify the array of the functions that he or she wants to trace, put it to the array, the size of the array, the BTF IDs count, and that's basically the full interface on the BPF side. We also need to change the attach layer. So there's new ftrace API. It's similar to the previous one. Of course, the only difference is that we actually need some way to gather all the functions that we want to change. We use the ftrace ops object, and there's already function in ftrace that can initialize the object with multiple addresses of the functions that you want to trace. Ftrace set filter IP is the name of the function. So basically, user calls we call this function in the kernel to initialize the object with all the functions that we want to change. And then there are the three new functions that are similar to previous one, just with the multi-suffix. We register the object with the trampoline address, and ftrace actually ftrace will make the attachment to all the functions which are now aggregated in the ftrace object. Same for unregister, it will turn all the calls to the knob for all the functions, and there's also the modify to change the for changing the trampoline for all of the functions. So how it all works together. So again, you load the program now with the new flag BPF F multifunc, and you create the link with that program, and in that link you specify the IP addresses of the functions that you want to attach, and it does all the magic. It prepares the trampoline and initialize the ftrace objects with all the IP of the functions, and calls register ftrace direct multi. The ftrace does the job of initializing, of setting up the ftrace with all those new trampolines, and all the RCU sync timeouts are called as well, but we are in single call function, so we don't actually care. So that's how the new interface works. So this was actually the nice and easy part of the presentation. So this is how it should work. Now I will describe some of the issues that we actually had along the way, and which will be hopefully addressed in the next post. I will start with the first issue we actually had with the batch attachment, and that was that if you attach any BPF, any BPF tracing function, any trampoline, then the ftrace graph tracer wouldn't be able to work over that function because they were just not compatible. They couldn't attach to the same function. And that was actually a problem because now we would allow with this batch interface to attach to thousands of functions. And if any user wanted to run the ftrace graph tracer at the same time, those functions would be disabled. So there was actually the solution. Steven actually got already some proof of concept patches ready, so we just rebased them on the current code, and it turned out that it's working nicely. So after this fix, we could actually come and starting to work properly on the new batch API for the ftrace. Another problem is that till this point, every trampoline was attached to one single function. And now if you allow the trampoline be attached to multiple functions, now you have one trampoline that needs to serve all the functions that it's attached to. And that comes with the price. So as I said, this slide actually shows the current state. So for every attached functions, you generate one trampoline, which actually takes the arguments of the functions and prepares those arguments, prepares the stack for the BPF program to be called. So each trampoline needs to know just the model of the function, number of arguments, and types of the functions of the function that it is attached to. With this new API, you end up in this situation where you have multiple functions calling a single trampoline, which needs to call the BPF program and needs to prepare all the arguments from different functions which have different number of arguments. And moreover, if you have another single trampoline attached to one of those functions, now you have trampoline that actually needs to call program which expects all the arguments from all multiple functions, and another program that expect only specific arguments from that function. So basically, this is sort of problems that you need to take into account, because you have the generic trampoline for entry programs which expects only arguments lined up one after each other. It's not a problem. For exit programs that have specific interface that have the arguments, and at the end of the arguments there's the return value, it's a problem, because you have two programs, and like in this example, the first one having 4 arguments and a return value, and the other one expecting the return value where the first one has argument free. So these sort of things you need to deal with when you have generic trampoline. This is what we did in the first two posts, but it added really a lot of complexity to generating the trampoline. So we decided that's not the way. And Alexei had actually the idea that we could group together the functions with the same number of the arguments. So what you actually end up is like you have the set of the functions that you want to attach, and you group them by the number of arguments, and for those groups you create separate trampolines. So like in this example, you end up with 3 trampolines, and really in a generic way, even if you have multiple thousand functions, you end up only with 6 possible trampolines, because 6 is the maximum number of arguments that we support at the moment. So instead of attaching one single generic trampoline, we attach 3 of them, which is still not a problem with regards to attachment times. And we actually save a lot of complexity while generating the trampolines. Another problem, you can have, as I explained, you don't have just one generic trampoline. You can have multiple trampolines that solve the generic issues. But still, at the end, there is the BPF program. And the BPF program, you have just one program, and it's called from multiple functions. And it needs to know where it's being called from and what are the arguments of the function. So once the program actually realized, okay, I'm being called from this function, it knows which arguments to access, and it has to have the way to access the proper arguments. So this is solved by adding new helpers. To get the IP address of the function that actually called the program that's being traced at the moment when the program is executed, there's a new helper, BPF getfunc IP, and basically it returns the address of the function. And this is the only part of the packset that got already merged. Nice thing is that it's not just for tracing, but also for K-probe programs. And it works also for standard programs, not just for these new multifunc programs. So once you find out which function called your program, you can access the arguments. And for accessing the arguments, there will be 2 new helpers are in plan. 2 new helpers which will be posted in the next iteration. BPF arc and BPF red value. BPF arc will give you the argument value, and you specify like which argument you want to get. And BPF red value will get you the return value of the traced function. So this way, the program will access the arguments. Last problem is something I called mixing trampolines. So at the moment, when trampoline can be attached to only one single function, this is not a problem. There cannot be any mixing at all. But if you have situation where multiple trampolines share the same functions, you can end up in the situation like in this, I'm showing on the slide. So each rectangle is actually like the set of the functions that the trampoline is tracing. Each trampoline is attaching different program P1 to P6. And if those trampolines actually wouldn't intersect, you would have just 3 different trampolines calling the attached programs, and everything would be okay. However, they intersect, and we need to create a new trampoline for each of that intersection, because each of that intersection needs to call different programs. So this is actually another complexity that hopefully will be solved in the next post. The current status, as I said, there are already 2 versions of the patch set posted. They didn't have the complexity of mixing the trampolines. They were just denying that. But it basically on the review, Andrew asked to allow this possibility, so that will be part of the 3rd version. The patch set contains the fix for the graph tracer. It has of course, all the needed APIs for ftrace and BPF, and also the self-test. So hopefully, the 3rd version will come soon. And that's all I have. If you have any questions.
Yeah, does anyone have any questions for Jiri?
Yeah, I have. Great talk and great visualization, actually. The first question I had, like, if you can go back to the BPF link API definition. How do we distinguish between fexit and fentry multi-links? It didn't seem. So you have multi with BTF IDs, and that's it. Is it like fentry? Is it fexit? Do we allow fmodrat? What were you planning?
So that's something you specify in the expected attach type field, right? So that's actually, you say this when you load the program.
Oh, I see. And then can you intermix fentry and fexit? Oh, wait, it's one program.
Yes.
Okay, so it makes sense.
Yes,
All
it's
right.
another program. You load another program for fexit and call the link again on that program.
Okay, cool. Yeah, we can probably also extend the update link command to accept multiple BTF IDs and sort of like add, update, reset operations so that you can modify this set of BTF IDs. But we can talk about that, in next versions. We don't have to add it like from the very beginning. There's already a lot of complexity.
It was actually there before, I think, but I took it out because complexity was already too much.
One more thing that I wanted to mention, like, I don't know if you followed along, but I recently added this, what we call BPF cookie, where you can associate like U64 with any attachment, like with any link. Well, not any right now, it's like kprobe trace points and stuff like that. I hope that we'll be able to do this here, but specify like separate cookie for each BTF ID. I think that should be like pretty easy to extend, but just so that you're aware.
Okay, I will check on that.
Because like you mentioned the BPF get func IP, right? Like, which is useful to know like what's being called. In practice, that like you need to add like extra hash map lookup and all that stuff if you need like more than just IP, right? So the cookie is the way to cheaply and easily add like extra context for each specific attachment. So I think it will be useful in this case as well.
Oh, okay. I will check on that.
Yeah, cool. Thanks. Great talk.
Any other questions?
Yes, I was wondering, since this is specific, at least seems to be specific for K-Funcs and such, have you considered something similar for other program types, like for instance, tracing a large amount of trace points, something like that?
Right, not at the moment, but yeah, it should be doable. I hope this will be generic enough to be spread over other probes. So yeah, it might be possible if there's a need. So I'm coming from this use case where we actually need the trampolines in this BPF trace to be attached fastly. So yeah, that was the initial use case, but I believe the code will be generic enough to cover also other probes.
Okay, thank you. Definitely, I definitely will look forward to see this all land, because that would be a use case that we're looking at. So I'll definitely have a look at that once the code comes through. Thank you.
Great, thanks.
Masami Himamatsu, if you had some comments in the chat, maybe if you'd like to bring them up directly to Jiri right now, that would be great.
The chat is loading for me. I cannot see anything.
Yeah. I'll just read it out a little bit. I hear you.
Sorry, I need to enable the microphone. Yeah, I think thank you, Jiri, about the great presentation, and yeah, I think this is a good way to support the multiple interface event. Multiple the probes on the kernel entry and exit. Yeah. I have one question about this direct interface. So can I use this direct interface? It seems that because the direct interface can allow us to put some BPF probe function on the kernel, even a single kernel function, and the exit. So I guess I can use this interface from kprobes directly too.
So the direct interface was added to serve the BPF, but it does the attachment that I said. That's actually the work, like changing the knob to core. And I'm not sure. I think the kprobe attachment works differently, right?
Yeah. currently that the K-probes, K-probes, uses the F-trace if the probe point is used by F-trace. So that's our.
You are wondering if you can use this interface for K-probes.
Yeah, especially the K-ret probes. Currently, we have a K-ret probes, but I would like to replace it with F-trace or like a graph trace, because it can probe the function exit. Yeah.
So yeah, I'm not sure about the red probes, because both BPF and F-trace are doing it in a different way. Like BPF calls the original function by itself and then actually running the red probe, and the F-trace is hooking on the return value or on the return address, right? So.
Oh, I see. So yeah.
I'm not sure. There might be problem somewhere, but I would need to double check.
Okay. Yeah. Okay, I will check that the implementation. Thank you very much.
Thanks.
Okay, are there any other questions? All right, thank you, Jerry, for your presentation very much.
Thank you.
Okay, Joe, I've made you the presenter, so you can start whenever you're ready. Thank you.
Perfect. I'll start at 10:05. I'm going to rejoin the meeting because the echo test never turned. I can hear myself.
Joe, I can hear you. Can you not hear yourself? Joe, it says you're muted, dude.
Yeah, it's just waiting one more minute.
That looks better. Good.
Okay, I'll get started. So, hi, my name is Joe Burton. I work at Google, and I'm going to be talking about a proposed new capability for BPF that I'm calling BPF map tracing, and the use case that motivates it, namely hot updates of stateful programs. So this presentation is an RFC and a status update. I presented this work externally a few months ago, and I've been working on it on and off since then. It has been prototyped, and the stuff that I'm going to be presenting here can be sent upstream soon. But there's still some open questions that I want feedback on. And with that, so I'm organizing the presentation into 5 sections. We'll go over the concrete use case that motivates the set of kernel changes I'm proposing. We'll cover an abstract model of the problem and the solution. We'll cover the concrete kernel changes and some interesting selections from the source code. I'll cover my open questions, and then we'll summarize everything at the end. Okay, so first let's start with our motivation, which is a stateful program that somewhat surprisingly we weren't able to upgrade. So BPF DINEncap is the set of programs that we developed at Google, and we're actually going to be covering this in a later session at LPC. So if you want all the details, please visit that session. Hopefully I don't butcher it too badly. But at the highest level, what DINEncap does is it allows applications to dynamically specify the source and destination IPs that they want to use when encapsulating the packets on a socket. So applications can opt in a socket by invoking a setSocOpt, which we'll call a cgroup setSocOpt program. And then a TC program will actually perform the encapsulation. On the right-hand side, you can see a graphical representation of this. So we have our setSocOpt hook, a program that gets invoked. It writes some data into a map. And then when you actually start sending data, the TC hook will invoke a program which will read data from the map and use it to perform encapsulation. So the entire application uses 3 maps, and we'll go through them now. The first map is called DINEncap map. It's an SK storage map, which is a kind of local storage map. It records the IPs that should be used when we're encapsulating the packets on a socket. The setSocOpt program is what populates it, and the TC program that performs the encapsulation is what consumes the data in the map. So if we lose the data in this map, for whatever reason, the side effect is going to be that packets that are sent from that socket are not going to be encapsulated. So what user mode is going to see is they're going to see, I made my setSocOpt, it succeeded, I started sending data, and it was encapsulated for a while, and then at some point, it was no longer encapsulated. So losing the data breaks a contract with user mode, so the data in this map is absolutely critical. Next, we have a map called SYN_encap map. It is an LRU hash table, meaning that when it fills up, the last updated entry will be removed or replaced. And what it does is it stores the outer IPs of encapsulated SYN packets. So an encapsulated SYN will come into our C group. It'll hit our C group skb/ingress program. It'll detect if it's encapsulated. It'll parse out the IPs, and it'll put them in this map. Then when we start sending data back out on the socket, the TC program will look in this map. And if it finds an entry, it'll encapsulate using those IPs. So if we lose the data in the map, what's going to happen is that the TC program will drop a SYNAC. That's for technical reasons that I won't go into. It's just like how the implementation works. But the important part is that, we don't want to lose the data in this map, but if we do, we're going to drop a SYNAC. And so I believe that that means that another SYN will come in, and this time we won't lose the data, and we'll respond with an encapsulated SYNAC. So losing the data in this map is bad, but it's not fatal. And finally, we have a third map. It's called reflection status. It's a per CPU hash table. All it does is it counts up the number of errors of a given type. So the key is an enum of like an error class, and the value is an integer, just a counter. Our cgroup skv/ingress program is what mutates the data in the map, and a user space app is what consumes it. And it's essentially just for debuggability. So if we lose the data in the map, it really doesn't matter. It's not relevant to policy enforcement. So in summary, we have 3 maps. They all have different types. If we lose the state, each one has a different level of severity. And I kind of glossed over this, but also the way that we modify the state in the map in each case is different. The top one, we get a pointer to a cell, and then we update through that pointer. The second one, we do that kind of access pattern where we get a pointer to the cell with BPF map update element. And we can also delete using BPF map delete element. And then the last one, we do a lookup element. Sorry, I misspoke. The sending cap, we update and delete, so we don't get a pointer to a cell at any point. And then with reflection status, we get a pointer to a cell, and we also do an update. So the important part is that we have different types of maps, different impact of state loss, and also the way we modify them is different. But we're going to drill down on the din-encap map because it's the most critical. And we're going to think about how we can upgrade this set of programs. So this is the critical subset of din-encap. I covered some other maps. Those are used to implement additional features that we'll leave out for now. So we have 2 programs in red. Each one of them is attached to an event in blue, and we have a map in green. Yeah, we already kind of went through this. So naively, the way we can upgrade this is we can load a new copy of each program. Say we have a new version, and we can also load a new copy of the map. We can do a bulk copy of the data in the map, and then we can swap each of the programs attached to the events using a BPF link update. The problem is that, say at the red line, we start doing our upgrade. We do a bulk copy of all the data in the map from the old map to the new map. And then by pure chance, an application does a set sock opt. So that's going to invoke the old program because it's still attached, and that's going to update the old map. And then, that finishes and we continue doing our migration. Now we swap in the new programs, and it just so happens now that at this point we're done with our migration. Now the application starts sending data, and the new version of the program is attached. So we look in the new version of the map, but as we said just a moment ago, we wrote the data to the old version of the map after we finished doing the bulk migration. So the encapsulation program is not going to see this data. And that's going to break our contract with user mode, and that's a problem. So the ramifications of this is that we can't upgrade programs like this because it would introduce race conditions and the possibility of loss of state. And in certain applications like this one, losing state breaks a contract. Also, we can't roll back our agent arbitrarily since we can't reload our program, and because we can't afford to lose our state. So if we were to roll back our agent, say we roll out a new agent and a new program, and then we roll back the agent, well, now we have new programs and an old agent, and now the old agent has to know how to talk to the new programs. So we can solve that actually by, before rolling out new programs, rolling out a new agent that knows how to talk to them, waiting a few release cycles, and then rolling out new programs. Because then we can roll back our agent a few versions and everything works out because it knows how to talk to the new programs. But it adds latency to releases. And in my opinion, one of the worst side effects of this problem is that developers need to know about the problem and keep track of it. So I'd like to solve this and make it generally possible to upgrade stateful programs without loss of state. So that's it for the motivation. So let's go into an abstract model of the problem and of the solution that I'm proposing. So we're going to be considering how we can upgrade this program set. This is the same picture as we had a couple slides ago, except we removed the din and cap stuff and just made it more abstract. So we have two programs, each one is attached to an event, and we have one map. The program 0 writes data into the map, program 1 reads data and makes some decision based on that data. So now let's upgrade it. First thing we can do is we can load a new version of the program set. And because we haven't attached the programs to events, this has no effect. Next, and this is the crux of the proposal, we can attach a copy on write handler to the old map. Any updates to the old map will invoke this copy on write handler, which is a BPF program. This copy on write handler can then so it sees the data that was written into the old map and it can write it into a new map. It can perform any transformations to the data that it needs to. Say we changed the layout of a structure, or we added or removed some members. We can do that inside the copy on write handler and write it into the new map. With this in place, we can perform a bulk transfer of all the data in map 0 to map 0 prime. We can do this with an iterator. So logically, but okay, I'm kind of getting ahead of myself. So there are two edge cases we need to think about, because now we have two programs that are looking at the same map at the same time. The first edge case, the bulk transfer program is effectively going to iterate over a map. Let's say that we're looking at the 1000th element in a 1000 element array. And while we're in the middle of migrating that element, the 0th element is updated. If we didn't have the copy on write handler, this update would not propagate to the new map. But because it's there, it does get propagated. So this edge case is handled. The second edge case to think about is, say we start migrating the element of a map, and then event 0 fires. So yeah, we start migrating the element of a map using the bulk transfer routine. Event 0 fires and invokes program 0, which then updates this cell by chance. The copy on write handler could then fire. It could write this new data to the new map. Then we could be scheduled back into the bulk transfer routine, which could then overwrite the new data with the outdated data that it was looking at. So this is just an edge case we need to handle. Essentially, it's just a concurrency problem. So we need to be able to serialize access to this map. So essentially, an important detail is that we need to be able to acquire a spin lock in both the copy on write and the bulk transfer routines. But assuming we can do that, this should all work. Next, we can start swapping programs one by one. We have to be a little careful about the order that we do it in. In general, the way you would do this is with the topological sort of the programs according to their data dependencies. In this case, what that means is that we would swap in our data consumer, which is the new version of program 1, first. So we can see that its data dependency is met because I've been thinking of this in terms of whether the data in map 0 prime was written in the recent or distant past. If it was written in the recent past, essentially what happened is event 0 fires, program 0 fires, map 0 gets written to, copy on write handler runs, and it propagates the data to map 0 prime. Then event 1 fires, and then program 1 prime fires. It reads the data from map 0 prime, and because the copy on write handler propagated the data dependency is satisfied. So any writes that are done in the recent past are going to be present in the map. Likewise, if there was a write in the distant past, we go through the bulk transfer chain. The bulk transfer routine will have copied that data over, and so program 1 prime will have its data dependency met. So no matter what, it looks like if we follow this scheme, the data dependencies that program 1 prime will have will be satisfied. And now we can swap in our data producer. And at this point, we're basically done because we have migrated over to program set V1. There was no point in time where the data consumer's data dependencies were not satisfied. And we just have these extra migration routines attached to a map, which is written to by a program which is not attached. So now we can just unload those migration programs, and we are done. We can just unload the old version of the program at this point. The nice thing about this scheme is that we didn't make any assumptions about the maps, about the nature of the change to the map that we're doing. So we could change the capacity of the map. We could change its type, say from like an array to a hash table. We could change the layout of the data inside the map. So you have a structure with 5 elements in the old version, and you want to add a 6th element to the middle of the structure. You could do that with this kind of scheme. And I think you could do more. I imagine you could probably split one map into multiple or combine maps, but that's getting ahead of ourselves. So that's it. That's the theory. And so now let's talk about how we're going to implement it with kernel changes. So this is an example program that will be tracing the BPF map update element calls to a map called traced map. We have some syntactic sugar with libbpf that will essentially let you just automatically load and attach this program. This is a tracing program, BPF progdeck tracing. It has a context to a new structure, BPF map trace context update element. The structure, the type of the structure depends on the type of the update that we're doing to the map. So for an update, we have a key and a value. We can read them. It's read only. We can't modify this memory. We can apply any transformation that we feel like. I just used this function as an example that you can do whatever you want. Not that this is actually useful. And then you can propagate the transformed data to a new map. So the context that these programs can receive, there's one context for each kind of map update that is supported. The patch set currently supports BPF map update element and BPF map delete element. And in the open questions, we'll talk about how to handle more. But this is kind of what's done now because it's easy. So fundamentally, we have to be able to attach programs to maps. So we do this with a BPF link create. We have an enum, which has one value for each kind of map update that we can trace. And so there's one for update and delete element. We have a structure which takes that enum as well as the file descriptor of a map. And then when you're doing your link create, you pass in a pointer to this structure and the size of the structure for compatibility. So because we're attaching programs to maps, and completely arbitrarily, I felt like it'd be more useful if we could attach a list of programs to a map instead of just one. When we update a map from a program, we can wind up invoking a cascade of programs which update maps, which invoke more tracing programs which update maps. And so you wind up you can wind up having a graph of programs and maps related to a map. because of tracing. And if the graph has a loop, then we're in trouble because you'll just get into an infinite cycle of updating a map and tracing that update and then doing the update again. So simple example, this is a length 1 infinite loop where we have our tracing program. It's tracing a map called traced_map. So whenever there's an update to this map, we'll invoke this program, and we will update the map, which will invoke the tracer, which is this function, which will update the map. So it's an infinite loop, and we can't allow this. You can also have a longer infinite loop. We won't go through the example in detail. You can see we're tracing map 0, updating map 1, tracing map 1, updating map 0, and then you would just get into a loop of just updating and tracing forever. So when we are doing a BPF link create, we just have to do a simple depth-first search on the graph of programs and maps. So yeah, on the graph of programs tracing a map and maps being updated by the programs recursively. And it's a very simple depth-first search. I won't go line by line through this algorithm. But yeah, it's fairly efficient. At link create time, we can just make sure that this graph is a DAG. Cool. So we had to modify struct BPF map because now there's a possible list of an optional list of programs associated with each map. So we have this structure. It contains a list of programs, and it's RCU protected. Arbitrarily, we decided to have an array of these lists with one list for each type of tracing. So you could have one list for map update element, a different list for map delete element. We enforce a maximum length on these lists, just pretty much just because it seemed like a good idea. And that's what this array is for, just to make those length checks efficient. And then we have a mutex that protects writes to these two arrays. So readers don't need to acquire the mutex. They can just iterate with RCU primitives. Writers have to acquire the mutex. And then finally, we have a pointer to this structure in our struct BPF map. This is one weird thing I wanted to call out. We don't use a mutex to protect this pointer. When you instantiate a struct BPF map, we will leave this pointer to be null. And then when we attach the first program, we will do an atomic compare and exchange to populate it. The intent is that when we are when we're trying to figure out if we have to invoke tracing programs after doing a map update, we want that check to be really cheap in the common case. So we don't want to have to acquire a mutex to traverse into this pointer. The side effect of this is that once you attach a tracing program to a map, you can't null initialize this pointer anymore. Essentially just because you'd have to, well, yeah, because there's no mutex. That's basically it. So moving on. Sorry about the blob of text. I meant to upload in a newer version, and also this header. But basically, we have so we have these helper functions. BPF map trace update element is one of them. So it has the exact same signature as BPF map update element, and that's by design. And all it does is it will essentially check if that pointer is not null, and if it is, it will go into it and iterate over the list of programs that are attached, over the list of map update element programs that are attached, and invoke each one of them. Moving on. So to make adoption easy, we put some changes into the verifier so that your BPF program will have map update element and map delete element helper calls. We use the verifier to replace each one of these helper calls with logically BPF map update element and then BPF map trace update element right afterwards. So the way we do this is we save the arguments to the, say, update element on the stack. We invoke the update element. We restore the arguments. We save the return code. We invoke the tracing function. Then we restore the return code from the actual map update helper. And then we return. And because we're using additional stack space, we have to record that. Okay. And so that is it. That's all the interesting parts of the implementation. So now I just wanted to cover some open questions. So the most critical one by far is that, the stuff I talked about so far allows us to trace map update elements and map delete elements. And the way that we do that is we essentially, when you make those helper calls, you invoke tracers at the same point in time. The problem is that map lookup elements and also the local storage APIs return a pointer, and then applications will modify parts of the data using that pointer. So if we were to do a tracing call, if we were to add a tracing call right after getting that pointer, it wouldn't have the desired effect because, of course, the actual pointer could be updated later on, and the tracer would not see that update. So one proposed solution that I think seems like it would work is that essentially we would leave the invocation alone, and then we would find the exit point of the BPF program, and we would trace, we would invoke a tracer which takes the pointer as an argument, and then that tracer would have access to the most up-to-date version of the data in that cell. And then it could just do like a mem copy of the cell over to the new version. And we're thinking that we could do this at the source code level, because doing this at the instruction level, essentially, X is just a value sitting in a register. And then you have this entire program in the middle, and now we need to find that value again. And in general, it wouldn't be possible to find that. Like, the compiler would be free to just throw away the value right after this line of code. So if we were to add a reference to that value at the source code, the compiler would make sure that the value is, hangs around for long enough for us to use it. So yeah, anyway, this is an open question. This is just one possible solution, but it seems workable. Likewise, we're using the verifier to expand each map update and map delete. And we just unconditionally append these tracing calls right after them. I was wondering if that seems acceptable, if we should do that conditionally according to like a flag, or should we do this outside of the verifier altogether? Should we do that at the source code level instead of in the bytecode? Just curious. And finally, we conceived of map tracing as a way of solving this upgradability problem. And I'm just curious if this sounds useful to anyone else, especially for any use case that we haven't thought of. Now, in summary, so we're trying to solve the problem of unupgradable stateful programs by giving maps copy on write semantics. We define a set of helper functions which can evoke tracing programs that are attached to maps, and we can mechanically add them to programs either in the verifier or in the source code. And this is just a recap of those open questions. And thank you very much for your time. but I'll go back to the last slide. So are there any questions or feedback?
Thanks a lot for your talk. So Dave asked me to take over the Q&A moderation. So if anyone has questions, please unmute or type in the chat that we have. In the meantime, I would have a question, which is like if you update the like one of the programs where you already have like the new map live, and then later on you call this copy on update helper, for example, how do you handle the case where there would be a collision when there's already a new map element created in the new map, but the old one would still do some sort of an update on that particular entry? So do you like defer this decision to the migration BPF program where you have this copy and write handler and then say, okay, let's just leave this alone if there's already an updated version of it? Or how do you handle the data transfer for that?
Yeah, I mean, that would be my intuition. So I think essentially it would be a case where like program 1 prime actually updates data in map 0 prime. My intuition would be that the copy on write handler would have to make the right decision, and that whatever the right decision is would depend on the semantics of your application. In the concrete example of didn'encap, this isn't the case. The actual, this program 1 prime is a TC program, and it does just read. Yeah, I think I would have to think about that more, but my intuition would be that you would want to define your copy on write. You would want to define your copy on write handler to have the right semantics.
Yeah, makes sense to me. Yeah. Yeah, we're sort of dealing with similar issues. In the case of Cilium, for example, where we have a connection tracker and we have same sort of problem. How do you migrate from one connection tracking map with this particular data structure as values to another one, right? So yeah, we could definitely use this mechanism as well.
I mean, one thing I was wondering about as I was walking this morning was, skeletons are really popular. It came up. It seems like if you could have a skeleton, basically, I'm wondering, like, so, we can have this feature. We can make it possible to define a copy on write handler, but we still have to define them. I'm thinking that we would use like the BTF of map 0 and map 0 prime. Like if you had the BTF of both of these maps, you could imagine mechanically generating the right migration routine to carry the data from whatever, to migrate from one format to the next. So if you simply deleted a field, you could see how you could just define a program that like copies the data and removes that field and populates the new data and writes it into the map. I'm wondering if that should be something that we do at the level of like libbpf. Initially, I was thinking we would just do it with like, internal Google application code, but it could be something.
What if that field deletion was actually a field rename? So you would get like seemingly new field and also like the old field will disappear. How do you know that this is the rename? It's like,
yeah,
there's too much semantics there. I think that like it's impossible to implement this for like all possible cases correctly all the time.
Fair enough. Yeah. And also, I mean, you could imagine, adding new fields, right? What's the right default?
And I was wondering, like, have you tried to write like your existing programs with like existing BPF facilities in this way that like allow to migrate their state to different maps? So like, if you have array of maps, right, you can have like an active and a new map, right? And like the old program might start like writing to both with whatever custom logic your program has, right? And then like when you migrated everything, well, actually, when you activated the new program, then you can run the BPF element iterator that we recently added, right? And just like copy over all the stuff that wasn't updated in the meanwhile. Like, did you try to use that approach? Because it seems like we have enough mechanisms to support this generically without like custom new BPF programs.
I haven't tried that approach, but that actually does sound like something that we should consider before investing too much in this.
Yeah, so look at the BPF map element iterator that I think Encode implemented a few months ago. So that allows you to iterate one map and like do whatever you want with other maps, right? And in this case, probably the easiest would be like this program set v0 should just know about this possibility up front and have like array of maps where normally you would have just one map, which is like your active map. But then for the transition period, you just add second map there and like notify your program somehow so it starts to write like in both places and stuff like that, or maybe just one place and then look, falls back to the old one, stuff like that. But I think it's just we have all the generic building blocks to do this customly for every single program, because I think in most generic case you would need like custom semantics for like what does it mean to migrate one state to another one, right? Like as we just discussed, like new field is added. What do you do? What if you have few maps that have to be updated in coordinated fashion under spin lock, right? How do you handle that? It seems there are more questions than answers. And the other point, like you were mentioning the DFS to detect the loops, right?
Mm.
You use used maps. Just wanted to caution you, because used maps doesn't capture all the actually used maps. When you have map in map, you won't know which maps you are using. That's a pretty common thing that people forget, but you don't know all the maps in general.
Okay, yeah, that is blocker. So used maps, okay, the problem is that basically it's just not known. The set of maps isn't known at verification time. Well, I guess, but we're doing this at, okay, I'll take a closer look. That is, thank you for calling that out.
The other interesting question is maybe also like if you add something to the key itself, you have to sort of duplicate that value as well, and you have to have some sort of semantics in your BPF program, in your copy and write, that would do this, right? And the same also, like what happens if you roll back? I mean, I presume you would use the same mechanism here, and you would have to make a decision in that program, like how would you delete that if there's something, if you remove something from the key, for example, and there are different values for that new key that you would potentially have. That's
exactly.
quite tricky. Yeah.
Yeah, I mean, I'm imagining that this would be, I mean, the way that we define these copy on write handlers, there could be a set of restrictions that we would just impose when we can mechanically generate them. Yeah, I mean, essentially, that's why I was hoping we could use mechanically generated copy on write handlers using BTF, because then essentially the new version of the map is self-describing using BTF, and we know how to migrate between two valid opted-in maps using this mechanism. But yeah, like for the reasons pointed out, it isn't 100% generalizable. But yeah, I'm hoping that it would still be useful enough to be useful in practice. I mean, you could just say, you have to assume that certain fields are optional, right? When you add a new field, if you delete a field, that means that rollbacks might leave it 0 initialized or something like that.
Yeah, I agree. I mean, yeah, like the sort of the old programs, they would have to understand this structure where you would have to just create new ones and somehow merge this if there are multiple entries to it. But
I agree. I mean, I think like the migration probably needs to, like, can be done in with some simplified constraints probably, and this definitely needs to be taken into consideration. There was a question from the chat from Tech Shack. Wouldn't BPF map reuse by new programs help to retire old programs while keeping the BPF map persistent for the new program?
Yes, we're building that currently. This is essentially handling the case where we want to change the something about the map, like the type, the capacity, or the layout of the map, of the data in the map.
Yeah, exactly. Cool. Anyone else has any questions? Please speak up now.
So this map reuse thing that, like you're saying, we want to change like the size of the map and stuff like that. What about the changing of the key size and value size? You mean like change just like the amount of elements in the map, or the use case is actually changing the layout of the value or key?
So in the case where we're reusing maps, we don't permit anything about the map to change. Essentially, we get a file descriptor to the map, and then we use, I'm forgetting the name of the API. There's a way that you can override map relocations using libbpf. We use that to essentially pass in the right file descriptor when we're loading the new program, so that then this map 0 prime is essentially pointing to map 0.
I see. So you are not doing that like after the program is loaded. You're doing it before it's verified, right?
I'm sorry if I think I'm not understanding the question.
So when do you do this? So I think you're using like reuse map FD or something like that, right? Are you doing that before the new BPF program is loaded into kernel and verified, or
yes,
at runtime?
Yes.
I see.
Okay. Before the new ones, yeah.
And I think maybe like change, like, and at least for the case where you enlarge the map, it should probably be the more straightforward case, because you like if the key and value size and structure is retained, I think that's like it's like probably like a simpler problem to have, right? I mean,
so
yeah.
so if you're talking about doing that like at runtime, right? Because I think that's the most generic one. You already have the program, then you want to replace the map. I thought that was the use case, Daniel, that you mentioned, no? Well, anyway, my point was that when we replace map at runtime after the program is validated, right? A verifier does assumption about like key size and value size. So I don't see how easily we can just change the value size, because that might break the verifier logic essentially. Like, well, it will not break the logic, it will break the safety of the program essentially. Does it make sense?
Yeah, correct. Yeah, it makes sense.
Hard problems.
Okay, so I presume we don't have any further questions. In that case, I would like to thank you and for bringing this up. Definitely interesting topic, and yeah, thanks. Also, thanks to all the speakers from today. This concludes basically our networking and BPF track for today. Tomorrow we are back here at 7 a.m. Pacific time for the next batch of 5 talks. And after today's session, just as a reminder, at 11 Pacific time, there will be a keynote from John Maddock Hall in the for the general LPC that is covering like across all the tracks. So with that said, thanks everyone for participating and for speaking here. It was really great, awesome, and see you tomorrow. Bye bye.